All right, good morning. Welcome, everyone. My name is Alberto Salleo. I'm the chair of the Materials Science Department here at Stanford, and on behalf of the whole department, I'd like to extend a warm welcome to all of you who came here to spend the day with us today. It's great to see a lot of familiar faces, friendly faces, a lot of old friends. It's really great to see all of you here to celebrate the legacy of Bill Nix, the legacy not only to our department, but also to the discipline as a whole. And it's always amazing to hear how many people are connected to Bill one way or another. Every year, I meet more of them. I also hope that you mark your calendar. This is now with N equals 2. This makes it officially a recurring event. So this is the second Nix lecture. There'll be a third one and a fourth one and so on and so forth. So please plan on being here in the next years so that you can again meet your old friends, connect with new friends, and learn all the great things that are going on in our department. I want to give special thanks to everyone who's traveled. The weather was pretty bad in the last couple of days. You know you live in California when you see a Tesla floating down the street, and your first reaction is like, great, it's not a drought year. I can have a shower every day, stop collecting the gray water, and go on with my life. Unfortunately, because of the weather, we have a small change in the program. Craig Barrett's flight was canceled last night. He couldn't find a flight early enough to be here today. And so he sends his best to everyone, but unfortunately, he won't be able to make it, and we'll miss him. It's sort of ironic that we had this weather here, these extreme weather events. It also reminds us the major theme of the event and why we're here today. At this point, the science is pretty clear. Climate change gives rise to extreme weather events, and extreme weather events are also a symptom of climate change. And understanding and curbing climate change is one of mankind's greatest challenges for the 21st century. And materials are already playing a huge role in helping us address this challenge, and I think this role will only grow over the course of the year. And so today you'll hear from two of our faculty how their research addresses climate change. You'll also hear from our keynote speaker, Professor Steve Chu, how materials are an enabling technology in order to get us to zero greenhouse gas emissions, which at this point also the science is pretty clear will be needed if we really want to control climate change. The fact that our department is so deeply engaged in having an impact both in teaching and in research in such an important challenge is in line actually with the Stanford founding grant. I'm reading here that states that the university's goal is to qualify its students for personal success and direct usefulness in life. The purpose of the university is to promote public welfare by exercising an influence in behalf of humanity and civilization. So you see it's really important. It's really part of our charter to do this. And in fact, part of it, if you read between the lines, is to take leadership in this. And I think our department is really having a role in this. So this is all I wanted to say. You're not here to listen to me, but to our speakers. But before we move on to our first speaker, Professor Felipe da Jornada, while he comes here to the stage, I want to thank everyone who's helped us make this event happen. Our event manager, Chris Hall, in the back there, our department manager, Lisa Ewan, and the whole staff. This was an all staff on deck, all hands on deck type of event. So let's give them a hand to thank them for putting this event together. And it's my honor to welcome to the stage Felipe da Jornada.
Thank you very much. Well, good morning, everyone. It's really my honor to start this really exciting days of talks. My name is Felipe Jornada. I'm an assistant professor, and I joined Materials Science and Engineering, our department, in 2020. And I'm pretty sure they're going to hear about all the exciting research from Leora as well, and the department more broadly. But something I also want to highlight that maybe it's not as apparent is not only the kind of impact that our research has, but also how our department is also supportive and welcoming to assistant professor and so on. And from just talking to many people in the department, I really learned that this is pretty much also due to Bill Nix being such a leader and also creating a strong community and encouraging a supportive also environment for research to thrive. So really I want to thank Bill for creating all the infrastructure for success. So what I'll tell you about is, I'll tell you a little bit of my research, but I also want to tell you a little bit more of a broader perspective of some of the exciting research that is happening right now in materials discovery. So, and I tell you a little bit how recent advances in machine learning and AI are a bit changing the way that we can think about materials discovery. And at the end of my talk, I'll also tell you how that is connected to my research, also renewables and other directions. And the way I actually want to start my talk is maybe asking maybe a strange question. There's so much computation resources, so much excitement about machine learning. And the question is there truth behind that hype? Can we actually generate new materials? Can we actually make impactful discoveries? And if you think about that, it's actually not that obvious. A question like that was raised even 50 years ago. And the question is, what could you learn if you could simulate a material, say exactly, with all the atoms and all the degree of freedom? And this question was particularly raised by two pioneers of computer simulations, Marvin Cohen and Volker Heine. And basically, they were dealing with quantum mechanics description of electrons in the materials and so on. But their question was, if you could compute exactly the total energies in quantum mechanics of a material, what could you learn? And what they said is that you couldn't learn anything, or what you could learn won't be of the slightest use. You would at most agree with the experiment. And what they remarked is that if you actually want to make an impact, what you have to do is basically pick a few essential factors that explain your material and describing that in terms of simple but well-founded concepts. So the question is, if you make a huge calculation with 10 to the 23 atoms in a piece of aluminum, would you learn about the importance of dislocation and defects for the mechanical properties, or would you just get a very large number? So that is how I like to start my talk, and the end result is that, of course, it will be a little bit more uplifting. There is quite a lot that we can do. And the way that I'm going to show you how that is possible is the following. There's quite a lot of excitement right now in data-driven materials revolution, and that is really what caused this new paradigm when we're living right now. And I tell you about what I think is two revolutions that happened broadly in the field, using databases and material screening, and also generative AI for creating materials. And then I tell you a little bit more about really two research topics that my group has been exploring, which is related to do we actually have enough data right now for discovering materials, and how much do we have to push the boundary of how much information do we have to predict new energy materials and for addressing challenges in renewables? So let me start by telling you about this data-driven revolution. And the idea is, again, trying to address the question of whether computers can really revolutionize material science. And I think the key aspect here is to realize that if you have a single calculation, maybe very accurate, that will be an artisanal process. You will need a lot of human input to take that calculation, realize that, there is this feature here, maybe a dislocation or a defect that may be correlated with the property of their materials. But there's something qualitatively different that you have when you have enough data. When you don't have one calculation or 10, but when you have 100,000 calculations. When you have that condition, you can use algorithms based on machine learning to automatically find correlation and causality. And of course, we are used right now to this sort of period in life where I can use machine learning to do a variety of tasks. My 7 years old likes space, so he asked me to create a picture of a sunset and an exoplanet near a galaxy and a Saturn-like planet filling the sky. And we can do that very easily. And I can do that because there is a machine learning model that does that. But that machine learning model is only possible because we have databases that actually tag images with information, such as text. Now, in this case, all the revolution that we see in image generation, it is possible by the pioneering work by Fei here at Stanford, who created this database called ImageNet. So the question is what is the equivalent for materials science and engineering that is really allowing us to get to this exciting direction? And I'd say that the first really revolution that happened in our field was circa 2010 or so, when a few groups decided to take on the challenge of doing computer calculations that are accurate enough to address the stability of materials, using basically high throughput calculations using techniques such as known as density functional theory. And once they have those calculations, just maintain large databases with that kind of information. So when that started, they had maybe about 10,000 materials or so of characterizing a bunch of different families, oxides, sulfides, and so on. Right now, those databases contain about 150,000 materials. And to give it an order of magnitude, the number of experimentally known compounds in databases such as the International Crystal Structure Database is of the order of 40,000. So it's really exciting that we can now come up with structures. Anyone can suggest in the structure. A computer can perform calculations and tell you what is stable and some of the properties that you have. So what is the impact when you have that framework, like the database, just like ImageNet? So what happens is that you can do, you can start to predict materials that fit your desired specifications. And I really have to acknowledge the pioneering work from our previous colleague in our department, Evan Reed, who of course passed away very tragically 2 years ago. But he was one of the key players in setting a pipeline that actually discovered new materials. And the main idea is that if you have enough data, you can basically apply a bunch of filters, such as imposing the fact that your material is stable, or maybe it doesn't contain a few elements that may be toxic, maybe you want semiconductors and so on. And at the end of the day, you have that small bucket with the materials that are interested for your desired application. So this sort of technique can be actually quite generic and actually quite impactful already. So even if you simply screen and select materials from databases, you can easily find novel ionic compounds, cathodes for battery materials, new photocatalysts, thermoelectric materials, and so on. And many of actually these approaches have already been validated against experiment. Now, in this example with photocatalysis, they came up with 71 candidates. Experimentally, they managed to synthesize 11, and 6 turned out to have favorable band alignment for water splitting. Of course, not all predictions are actually achievable or potentially correct or useful, but it's much better than trying that at random or trying to use our implicit bias that may be avoiding a part of your phase space of materials that may be quite exciting. But the other revolution that recently happened is actually to use also this sort of techniques to understand materials that go beyond better materials and so on, but also what do you do if you have more than one condition that you have to fulfill at the same time? And one example that I want to give is a recent work that my student Akash Ramdas, he joined originally with Evan Reed shortly before he passed away. And the project that Akash has been working on is to finding a new material for interconnects. If you know the field, if you want to make transistors smaller, there are a bunch of challenges, making sure that you actually have a transistor that behaves at very small length scales. But one of the challenges that we often forget is that you can't even deliver electrical current at those specific pitch sizes when the features are small enough. Because you cannot make your interconnects, you cannot make copper smaller without sacrificing losses in a way that you completely melt or use all your energy budget just to cool your device. So the challenge is really, if you look at those stacks, coming up with materials that are conductors that can be very thin, that don't have a lot of surface scattering and so on. So it turns out that one can also find new materials. It's actually quite exciting. But unlike traditional approaches, one cannot just optimize for one property. One is interested in having materials that are broadly compatible with your CMOS kind of depositing framework. They have to have, of course, a large bulk conductivity, and they also need to have a small scattering time. And to give an idea, in those dashed curves, if you can see, you have in that plot, you have ruthenium and copper. Copper, of course, is state-of-the-art. Ruthenium is expected to be one of the candidates that is beyond copper if you make copper smaller, because, of course, copper oxidizes and has a large surface scattering time. But there are few materials that we predicted that turned out have reasonable bulk conductivity, maybe not as large as copper, but have a very good also surface scattering time, which really make them promising materials for interconnects. And besides that, we can actually use computational techniques, not only to say that these materials may be useful, but actually accurately compute how the mean free path of electrons behave over the whole Brillouin zone and have a much more accurate prediction so that experimentalists can really, our colleagues can actually synthesize that. The end result is actually we did convince experimentalists to synthesize these materials. And if you want to hear about the result, you have to go to the poster session by Akash also during the break. I lead a little bit of drama maybe for these results. But the other kind of very exciting revolution that happened in materials discovery is not only can you screen materials and find your set of compounds that have the properties that you desired, but can you somehow expand that phase space and come up with other materials that you think are also going to fit the bill, but which you haven't computed before. There is no entry, there is no experiment, and there is no database in which you computed those materials. And this is really one direction that has been quite impactful in the last few years, thanks to machine learning and similar techniques. So the idea is the following: how can I come up with materials that have some desired properties if I haven't generated that before? And the idea is that I have to come up with a model, basically a model that tells you how you relate a crystal structure to a property. And if you want to have a mathematical model, such as based on machine learning, I need to encode that crystal structure in some mathematical form. Now, and if you ask the literature, there are a bunch of different flavors and how that can be done. You can take a crystal structure and ask about what is the overall structure. You can try to represent that in terms of a graph. And it turns out that even a very simple technique, such as taking all the atoms and doing a mean of the atomic number and rows and columns of the periodic table, number of electrons, and things like that, actually give you information that can be used for training machine learning models. So whatever you do, you can use that information to transform your material into a set of numbers, namely a vector, as I showed that on that vertical stripe. And that vector is associated with a property that you compute, red box. The question is that how you relate, given any vector, what is the output? And this is something that we're quite fortunate that there are so many machine learning models that have been developed by industry that allow us to connect that. So in the traditional framework, the way that we discover new materials is that we basically train a model to predict properties given this feature vector, this material encoded in a mathematical way. And then how do you come up with new materials? It turns out that this is surprisingly a simple and pragmatic approach. You basically guess structures. Most of the techniques actually take your crystal structures, you change the atom kinds, maybe distort the positions, swap the positions, and as you change or try a new formula, you apply that to the model, and the model tells you whether that is stable or whether that should have the property that you expect. So it's actually a quite powerful and simple technique that you can use to come up with new materials, and that actually has already been quite impactful. Some of the recent work in the community, just to highlight some even at Stanford, the previous group by Evan Reed also come up with new lithium-ion conductors that have been actually validated by the group of Will Chu here at Stanford. There are also new ultra-bright materials for photocathodes, which is quite exciting because that is potentially, if you have a material that is super bright for either free electron sources or photocathodes that is resistant to air, that kind of material can actually save $1 billion in those sort of facilities. So it's also quite exciting perspective. And also one project that I've been involved with is even finding materials that may be quite unusual. Materials that are synthesizable, that are stable, but they have a wire-like structure, as you can see from the bottom right figure that I have. Now, and computationally, people knew 700s of materials that behave like that, but also using machine a model. Now, my previous student, Yangbin Su, who was also with Evan Reed in the past, and we come up with ways to generalize that to over 30,000 materials or so, and some of which has been validated by experiment, and those sort of materials can be quite nice for really high one-dimensional transport application and also magnetic properties. So you may also have been aware of the excitement not only in materials generation, but some of the press coverage that some techniques have had in the last few months. So the teams by Google and Microsoft have also joined this exciting era and come up with models for generating new materials. Just to highlight 2 recent efforts, one is called GNOME. This project GNOME basically discovered 2.2 million new materials that they predicted to be stable. So to give a perspective, we had before 150,000 materials in databases. So they really expanded by 1 order of magnitude the number of proposed materials. So it's really an exciting prospect. But what I think is really surprising is also, if you look at how those techniques work, they're not qualitatively different from the techniques that I discussed before. You come up with a very good model. You are smarter with the way that you come up with structures. But fundamentally, you guess structures and come up with an answer, whether that should be stable or interesting. And another technique that also been recently gained traction is using diffusion model. So diffusion model is those techniques used by ChatGPT and image generation, which basically says that you start with some structure, and you keep adding noise to that, and you train a machine learning model to remove that noise, with the hope that if you start with a random configuration that is pure noise, you can remove that noise and come up with a material or one image or one text that has the answer that you're looking for. The excitement around this direction is that we have a prospect of not only generating materials, but materials with the property that you're interested in. So just like ChatGPT, we can actually right now create materials with text saying, I want to generate a material that has high electrical and low thermal conductivity. So for thermal and materials discovery and applications, it's really an exciting prospect. There was one caveat, however, in there, which is that we rely on training data, just like I mentioned from ImageNet. And the question is, how good is our training data? It would be very good if I can say, I want a material with high electrical and low thermal conductivity, but we don't have that information in training sets. Most of the training sets have as information the energy, whether that is stable, and the band gap, even though it's often wrong. So we actually have a lot of work to do in that to have actually impact in energy materials. So I would like to end the first part of my talk by just highlighting some of the exciting but pressing challenges that we have in this direction. One is that with the current approaches, computation and theoretical techniques can generate a bunch of materials that may be quite exciting, from interconnects that I just mentioned to novel cathode materials and so on. But being able to come up with that pace and synthesizing that is non-trivial. So there's a lot of effort to some degree automate the experiments, but that's been quite challenging, especially because there's so much domain knowledge that is hard to translate to an automated devices. And the other challenge, which is absolutely gigantic, is that because we predicted one material is interesting, it doesn't tell you whether one can synthesize that, and it doesn't tell you how to synthesize that. So even coming up with models that say what are the precursors that you need in order to deposit that, those are huge challenges that we're just in the infancy of being able to address. And likewise, I mentioned database and so on. This density functional theory that I mentioned is often not a good enough ground truth to understand materials. And I want to spend 3 more minutes or 5 more minutes or so to tell you a little bit of what that means and how my research also fits this context. And also how one can understand now optical properties of materials, transport properties, and how this can be so impactful now on materials discovery. So there's typically a trade-off between accessing materials property accurately or being able to access longer time scale or longer length scales. On the left-hand side, you have basically quantum chemistry approaches that tend to be very expensive but very accurate. On the right-hand side, you have force fields, molecular dynamics, dealing with materials as mass and springs and so on. Most of material science and all the computation discovery uses what is known as DFT, that is known as density functional theory. It's actually super popular and underpins modern material science. There are over 40,000 papers per year that use this technique. The cost is non-trivial. It scales with the number of atoms in your simulation, typically to the power cubed or squared. But importantly, the accuracy is also limited. You can only access total energies and similar features. If you actually want to understand, for instance, what is the transport power property, what is the optical property of material, you have actually to use other techniques, One of them that my group specializes is that many-body perturbation theory, which unfortunately scales with the number of atoms, much worse, 4th or 7th power. But I know what is really exciting is that we have these techniques that allow us to compute right now optical properties, and they're very important for discovering new materials. Just to give you a perspective, there are a new family of materials that are atomically thin that have an amazing light matter absorption. You can make the strongest ultra-thin photovoltaics. You can see here the absorption spectrum. If you hit at the exciton resonance, you absorb almost 15% of sunlight, and you can actually deliver that as a power at the end of the day. However, if you use DFT and similar theories, you get that red curve that I'm showing you. You don't qualitatively explain the experiment. And what you're missing is the fact that when you shine light, if you remember optical properties of materials and so on, you create bound exons, right? Correlated electron hole pairs. They really dominate the optical properties. So we need really to include that to understand what is happening in those materials. But what is exciting is that with the recent efforts, we've also been able in our group and other communities really to make those calculations much more accessible. So for instance, my student Aaron Altman and postdoc Sudipta Kundu also developed a method that you make the scaling go from n to the 4th power to n squared or n cubed. So that really allows us to scale systems and compute materials with 2 orders of magnitude savings in computational resources. And that really allows us to study much larger materials, more realistic, and so on. So as one example, there's a lot of excitement also of taking 2 materials and stacking them one on top of the other. And what happens if you take one material and another atomically thin material and put them one on top of the other is that there is a significant reconstruction in the crystal structure. You form a superlattice, as I'm shown over here. And if you shine light, your light or excitations will be localized in the superlattice in some domain. So this can be really quite useful for quantum information application, creating single photon emitters, and so on. So those are also some techniques that for which we really need those techniques. And just to highlight some recent efforts, my also student Jonathan Gregoras recently worked on, is that these sort of excitations you can really think as something analogous to a hydrogen atom. There is the binding between the proton or the electron, in this case the electron hole, and you can calculate that also without fitting parameters very accurately. But we can also ask in those materials where those excitations get localized. And it turns out that they're quite localized. They're localized enough that it almost looks like your material behaves like a trapping potential for those excitations. So this reminds me quite well of some of the pioneer work and Nobel Prize by Stephen Chu of cooling ultra-cold atom. Because to some degree, what we're saying is that you have a material, and that material can behave like an atomic trap. And you can use that for quantum application, sensing, and so on. And of course, all this exciting result has been really been leading to other kind of validations and also work that we've been involved in the literature. I do want to mention that maybe out of time, I will skip a little bit of the machine learning aspect of those materials discovery. But I do want to mention that we're also not only interested about how optical properties can be used for quantum applications, photovoltaics, but also broadly speaking, how can light and excitations change the way that your materials qualitatively behave? And I'll give you one qualitative picture, an example that I think is quite interesting. If you ask yourself how much energy it takes to take a hydrogen out of a titanium surface, well, that's a prototypical problem for photocatalysis. It turns out that it takes about 5 eV or 6 eV to remove this hydrogen from the surface. If you shine light in your system, and my student Aaron Altman recently did that, it turns out that the barrier is much smaller. You can reduce the energy by about 3 eV and qualitatively change the potential energy surface of a material. So this is exciting because you can qualitatively drive different chemical reactions and potentially deliver energy for chemical reactions in a much more targeted way than if you were just trying to ramp up the temperature and ask entropy to make your reaction happen. So broadly speaking, we're very excited about all this field of course, how we can use massive computer calculations now with millions of cores, either combined with AI and other techniques to understand energy, materials, and quantum materials and beyond. And we think it's actually quite exciting also to ask not only what materials are exciting per se, but how you can engineer materials growth condition and green chemical reaction routes by driving your material out of the equilibrium zone. And I think that this is quite inspiring if you think that for the last few centuries, we typically think about material stability as a phase diagram. There's P versus T, and this is what I can access. And what if I tell you that somehow we now have a new axis, the energy axis? If I shine light in our material, maybe I can access metastable materials that are not even possible in the ground state, or chemical reactions that are indeed much more efficient and use less energy to create, say, renewables or solar fuel conversion that is otherwise possible. So with that said, I'd like to acknowledge some of the funding agencies in my groups and all the students that have actually, and postdocs that did the hard work. And let me thank you all for your attention. So I guess, do we have a few minutes for questions? Yeah, I'd be happy to entertain any questions if anyone in the audience has. Yes?
Thank you for a great talk. I find this area really interesting because having worked in a lab, it's very painful to synthesize materials. So if we can shortcut that, great. It seems to me like one of the challenges would be when you're taking input data on materials in general, you have, I work in optical materials, so think about ellipsometry data, like refractive index, things like that. A lot of that data, even for perfect materials, is technique dependent for the results that you get, or around, maybe there's surface defects that will affect this. And so if you pull all of the data for those kind of materials into a database and try to synthesize something, try to come up with a list of material possibilities from that initial dirty data set, you might end up with some things that are not what you'd expect, just based purely on the noise from the measurement side. How do you think about the inclusion of data on the input side and the sources and whether materials are bulk versus smaller, micro scale? I just wonder if you could expand on that a little bit.
Yeah, absolutely. That's a really great question. And to put that in context, these sort of materials project and databases, one of the impacts that they had, one of the key foundation was that not only they had a calculation for 150,000 materials, but of course it's perfect, so that simplifies, but also it's done by one group with consistent parameters. What you mentioned about defects and so on is not only depending on the maybe grad student that is doing the equipment that they're using, what part of the world they're doing, what is the humidity. So it's really hard to also unify that. But there is a lot of push right now to at least collect the data so that we know how much that works or doesn't work. So right now there are a bunch of efforts, such as at Argonne there was an effort to automatically capture metadata if you do any sort of diffraction experiment. Here at Stanford we have a proposal also to have an automated lab so that if a student picks up a screwdriver that is automatically tagged, if you take a spectrum, it's automatically tagged, so that we have at least more data. So I don't have an answer, but at least the answer that I have is more that we have at least to consistently collect data and get at most metadata as possible so that we can at least do analysis and try to address how much those different problems are indeed an issue, because we actually don't even have data to address that. It's really limited information. One more.
Hi, very nice talk. In your opinion, which of these materials would be closest to a real application? In a practical sort of way. You showed a lot of the 2D materials, and before that you were showing thermoelectrics, catalysts and all that. So which of them are closest to being practically making an impact, in your opinion?
Yeah, that's a great question. Of course, there's always a delay between coming up with a material and then actually integrating that. But actually, when I did my PhD, I was studying 2D materials, and I thought that they were very nice, interesting, but it would take maybe a few decades for them to actually be able to be used by industry. But I'm actually quite surprised. TSMC right now is working with 2D materials right now. Their challenge is not whether those materials exist, whether they're stable. It's more of, can you synthesize that in a low enough and deposit in a low enough temperature that it can integrate that with existing fabs infrastructure. So I do think that even 2D materials for electronic properties may not be potentially shouldn't be quoted on that. I don't know if they're recording me, but maybe 5 years or so, I think that we could already have an impact in even having prototypical devices and semiconductors that utilize them. And likewise, for the battery discovery, I think it's also quite exciting. It's a qualitatively different field. It depends also stability and longer-term issues of, is it stable? Will it explode? But even in that case, machine learning has been quite important. We will choose group have even techniques of speeding up testing protocols, and even in that case, there's a lot of impact on how you use machine learning to discover new battery materials.
Our next speaker is Professor Leora Dresselhaus-Marais, and she will tell us everything about the science needed to decarbonize manufacturing. Let's welcome Leora.
Thank you, Alberto, and thank you all for coming here. It's a real honor to get a chance to speak at this Nix Lecture and to follow Felipe's excellent talk, getting us started with AI. So I'll be talking now about the work that I've been doing in a slightly different area, looking at how we can use material science to be able to access things as small as nanoscale materials, all the way up to as large as full steelmaking reactors that are 10 meters wide and tens of meters tall. So perhaps we'll start off with manufacturing as a whole. If you look over the history of kind of human civilization, what we find is that it has been the major innovations in manufacturing that have kind of transformed the quality of life that we see in our society as a whole, from the Industrial Revolution and the widespread access of steel to the generation of our electrical grid, and eventually now looking at integrated circuits, robotics, automation, and now towards sustainability. But looking towards that sustainability, we see that there are a lot of inefficiencies that we have that have been, built into our system as we revolutionize process after process after process, that in fact, we really now very urgently need to correct in terms of climate change. So in particular, you can see that if we look at the greenhouse gas emissions over the entire planet, that we have absolutely a lot to decarbonize, but I'm going to focus today on the work that we need to decarbonize in the industrial sector. So to do this requires not just that we clean up the technologies that we have, but in many cases that we actually redesign things from scratch that are old processes that we are really, really good at today. So in my group, we come from a background in chemistry and optics and material science, and we design the next generation of microscopes that allow us to see important problems from the really, really basics of controlling strength, refining processing, to some of the more applied aspects of material science, looking at how we can make steelmaking and metals extraction become more sustainable, to, at the very end of the supply chain, looking at how we can 3D print metals to be able to make technologies that are more efficient than ever have been possible before. So I'll be talking today about my more applied points of research in the group, but I must admit, being able to give this talk at the Nix Lecture, I couldn't quite help myself from talking about dislocations just a little bit, as an honor to Bill Nix. So over the past 6 years, I've actually done a lot of work on dislocations, inspired by a lot of the really seminal work of Bill Nix. So I realized that actually there was no microscope that could watch hundreds of microns beneath the surface of a metal, how dislocations behave from time scales of, pretty slow dynamics like we see in annealing to really, really rapid dynamics like deformations during shock waves. So I went off and designed a microscope that, by imaging with just a lens and a detector along the X-ray diffracted beam, we were able to watch directly the strain fields that emanate from dislocation cores. So over the past 6 years, of course, this isn't so trivial. We have developed the toolbox to be able to do this. The ultra-fast X-ray technique, the building the microscope itself, the automated tools to be able to align that microscope, the optical theory to understand what the images even mean, and then the computer vision methods to be able to quantify what that information shows us. And so this has allowed us to start to get insights into what the behaviors of dislocations are deep, deep, deep inside of macroscopic materials in ways that are now starting to open up exciting directions in my group that I hope you'll go and check out some posters from my group during the poster session about. So we've been able to, at static timescales, look at the hierarchical networks of dislocations. At slightly faster timescales, we've started to look at how the fundamental stability of dislocation boundaries breaks down just at the cusp of melting. And at much higher timescales, we've been able to start to watch how strain waves, in particular sound waves or acoustic waves, interact with dislocations, generating kind of the thermal or the microscopic origins of thermal transport and thermal diffusion. And more recently, we've been able to demonstrate how dislocations can actually move faster than the speed of sound if you push them in just the right way. So now I'll focus the rest of my talk on extending this to more applied types of systems so that we can understand how to decarbonize important processes towards a sustainable future. So, of course, when we talk about metals, it always starts with steel. Steel is completely ubiquitous in modern society. It is 90% of the metals that we manufacture on this planet. It is intrinsic to so many of the technologies that we use, including the building we're in right now. But if we look at how exactly steel is made, we find that actually making steel accounts for 8% of the global CO2 footprint across every single industry. And it turns out that number is actually still going up as the demand for steel increases every single year. So we can ask ourselves, what exactly gives rise to this? And it turns out there's one step of this process that is responsible for over half of that carbon footprint. And that is just the process of taking our iron ores already processed and turning that into iron metal that we can then start making steel with. So if we look at how this is done today, we suddenly realize this is maybe no surprise, as the iron making that is done today has been developed for over 2,000 years using coal. So using coal, basically we are undergoing a whole bunch of carbon to carbon dioxide reactions, generating heat to get up to 2,600 degrees Celsius in the center of our reactors. And using these blast furnaces, we can generate incredible amounts of iron very, very efficiently. So today, we do this going from hematite to magnetite to woostite to iron, generating at least 3 molecules of CO2 per single atom of iron. And of course, there's quite a bit more going on because this is not a completely efficient reaction. So, of course, hydrogen is, all the buzz today. Hydrogen could, of course, decarbonize this process. And in fact, the first plant to try it opened in 1954. But it turns out it's not that easy because this makes an exothermic process become 4 times more endothermic, which is a really difficult problem, especially as you scale this problem up to the 1.96 gigaton per year industry that is steel as of last year. So when we look at, the multi-scale version of this process, this is multi-scale in a way that goes a little further than dislocations alone, of trying to understand how mass transport, heat transport, and atomic flux interplay from the perspective of single atoms to the single pellets we put into our reactors, to the entire flow of the reactor itself at the macroscopic scale. Macroscopic being tens of meters, of course. So in my group, we've looked at this problem from a slightly different perspective. We noticed as we dove through all of the literature that this problem is typically dealt with at very, very large scales. But we got some ores, and we very quickly identified that there are a lot of nanoparticles in these materials that are actually used industrially today. And so we scratched our heads as material scientists and said, well, chemistry doesn't exactly happen the same way in a nanoparticle as it would in a macroscopic particle at the millimeter size. So we went and we decided to zoom in on the chemistry of those nanoparticulate particles to explore how the chemistry of this problem is different at that really, really nanoscopic scale. So of course, when you're dealing with something that's multi-scale, you have to zoom in on the scale you're interested in. So we found a collaborator who was able to make us some perfectly spherical particles of magnetite, which is the dominant ore in this country. And we were able to do a quick study to at least validate that, yeah, with X-ray diffraction, we can see that the chemistry is nominally the same, but quite a bit faster in the nanoscale, as you might expect. And so then we went to the synchrotron to try to get more information about this surrogate system that can give us detail at the nanoscale about how this system is reacting. So we went to the advanced photon source to be able to set up a much smaller version of an iron-making reactor. And here we were able to do operando scattering to watch in real time how this reaction unfolds. So we were able to collect wide-angle X-ray diffraction that showed us the crystal structure, the phase that we were generating. And we were able to collect small-angle X-ray scattering at the same time, which was able to give us information about the statistics of the sizes and the shapes of those grains that were forming as the reaction unfolds, to get a picture of how things like sticking that would cause a reactor to completely stop running would happen and couple to the chemistry that happens. So, kind of a bird's eye view, this is what we saw, that going from 800 to 350 to 300 Celsius, you can see a dramatic decrease in the rate of the reaction, but at the slowest rate, you can see that actually the reaction slows down sufficiently to separate the mechanistic steps. So we were able to then, using some analysis software, decompose this into information about how each phase grew in and out. And very quickly we noticed that in fact, actually, it doesn't happen the same way on each facet of the crystal. We'll get back to that in a little bit, but to start off with, we were able to, at the very least, look at all of these different trends in, taking the derivative of to get the rate of formation, and this showed us that there were kind of three representative time scales over which this reaction was happening, describing different mechanistic steps. The first of these being really fast chemistry for all reaction stages. Then the second being primarily conversion of the first step, the magnetite to the hematite, magnetite to the wüstite. And then finally, the steady conversion of both of the oxides to iron. So looking a little bit closer at this from the perspective of the crystallography of the system, in fact, it's pretty well known in nanoparticle chemistry that the rates of reactions often depend on the crystallography of the system, as there's a really high surface to volume ratio, and the surfaces don't all have equal energy. So, for example, in the world of hematite chemistry, this has actually routinely been observed in photocatalysis as a very important aspect of why photocatalysis happens to occur best in certain shapes of nanoparticles that amplify the most reactive facet. So using this information, we were able to validate that there's this faceted trends with the surface energy that implies that our mechanisms that are going on here have something really critical to do with crystallography that, of course, we never think about when we're thinking about these big, huge reactor scales. So with small angle scattering, we were able to then tease out a little bit more information beyond just the fact that chemistry does not happen the same way in each direction. In fact, we were able to, with small angle scattering, demonstrate that the size changes quite drastically as we go from the purple initial to the red final. You can dance the rainbow and see the increasing size scale there. And effectively, by TEM, we were able to validate that at low temperatures, this is effectively a sintering process. But as we increase the temperature, we start to see this really dramatic shift to larger size scales as we start to see these larger grains beginning to form. And then ultimately, by the time we get to 400 Celsius, just slightly above this weird transition in the rates that we showed at the beginning, we start to form these, what we lovingly call nanoworms, that are incredibly long and oblong in shape, that are kind of reminiscent of the whiskering that's actually in an industry known to shut down the reactors and cause them to fail completely if this sticking problem occurs. I pushed the wrong way. So we looked, we scratched our heads and said, as microscopists, what can we do to get a little bit deeper insight into what is going on here and how this chemistry is coupling to this type of change? So looking by TEM, we did some interrupted studies, and we were able to show that actually the particles first self-assemble before they eventually sinter into these whisker-like products. And this has some suggestions about kinetics competing with mass transport and potentially some interparticle forces stabilizing some of the phases. But of course, we wanted to dig a little deeper as X-ray scientists, so we went to do what's called X-ray tachographic tomography, which allows us to look in 3 dimensions with sensitivity to the phase, but also deep in the 3D as a tomographic image with down to 18 nanometer resolution. So before I show you the results of this technique, we're going to talk a little bit about what the signal means, and then we're going to get to that point. So effectively, with tachographic tomography, what we're looking at is the progression of this sintering process based on an increase in the electron density of the system. This can happen because of increased packing density, but also because we're reducing the oxides themselves. So, of course, we would want to create a histogram to understand what the distribution of electron densities are to try to predict whether we're looking at packing density changes or true reduction. So we built a few types of geometric models, and we're able to validate that, in fact, there is a cutoff point beyond which it could never be an oxide. It could only ever be a metal. And what you'll notice is that this mysterious 2.5, the red histogram in the middle, shows 2 humps on it. One hump that is characteristic of sintering to the densest possible oxide, and one hump that is showing us something that's very characteristic of chemistry, indicating that there is actually a coupling between these 2 processes as we're watching them. This becomes even more dramatic when you actually look at this in real space. So we started with particles that nominally don't really have any preference. It's kind of a bunch of particles squished together. But as we increased in time, suddenly we saw the formation of these nanodomains. And you'll notice, if you look closely, that the switch from blues to oranges is exactly the cutoff from oxides to metals, meaning that what we're seeing is nominally something that looks quite a bit like nucleation and growth of the iron phase in this highly sintered region of the material. And then, by the end, we can end up seeing these final elongated iron structures that truly are metallic iron, but that have now increased in length scale by at least an order of magnitude, in many cases 2 orders of magnitude, because of this sintering, or as we call in the business, sticking process. So, how has this changed our view of the iron-making reactors? Well, what this shows us is that the stages of this chemistry at the nanoscale are quite different. That we have stage 1 of this surface chemistry, surface reaction, everything going to completion. because of fast mass transport. But then once we create a passivating layer of iron at the top surface under this reduction environment, we now have a diffusion-limited problem that turns into a Fickian transport law that drives the chemistry as an internal reaction interface. And then eventually, we find that this turns into a sintering problem that ultimately gives rise to this particle coalescence and generates the sticking problem even without macroscopic pellets around, as is usually proposed to cause the reactors to fail in the iron-making industry. So what our work so far has really demonstrated in this first study that we've done is that there are really important key insights looking as material scientists at the nanoscale to understand these really, really massive processes and how to be able to overcome some of the major shortcomings in this process. So in the short amount of time I have left, I'll show you a sneak peek of kind of some of the newer work that we're also starting to do in microscopy, looking at additive manufacturing. So now that we've looked at making steel, you can now ask yourself, how do you manufacture the parts out of steel? Manufacturing metal technology has been done for millennia of time, but is often inefficient in many ways based on subtractive manufacturing and having large amounts of waste, or in some cases simply based on machining tools, brittle to ductile transitions and things like this. So metal additive manufacturing has started to enable these unprecedented versions of design flexibility, where now using a laser or an electron beam, we can 3D print the structures with almost arbitrary flexibility and design complexity, basically from the ground up. But there are a few challenges to and a great demonstration of this is the GE rocket that actually, this is a rocket engine that they made all out of a single piece of metal, which normally would take hundreds of pieces of metal all soldered together and things like that. So it offers a really unique capability for this new direction. However, this type of really, really rapid solidification and then reheating, remelting creates a lot of variability in the parts and geometries that are poorly understood as compared to our thousands of years of classical casting and forging. So when we look at this from the perspective of the science that's happening, we find that this is actually a hugely complicated problem where we have multi-physics situation of this really intense laser generating these incredibly hot thermal fluids that flow based on mass and heat transport that generate these phase transitions and complicated solid mechanics problems that are ripe with all sorts of fundamental science gaps within them. Synchrotron science has really transformed this field since it was first done in the 2010s. By looking through the metal with X-rays, you can effectively watch in real time how the laser is melting the metal, generating defects, and in some cases also generating cracks. But it turns out the length scales and time scales that have been explored have always been limited by the brightness of the X-rays. So we recently, this is hot off the press as of November, we got a chance to do our first experiments, or the first experiments doing metal additive manufacturing at the X-ray free electron laser just up the hill, where using the brightest X-rays in the world and the fastest pulses of X-rays in the world, we were able to image directly how this metal additive manufacturing process is going down, looking at the fastest timescales and the highest spatial resolution ever seen in this process. So I wish I could show you more detailed data, but we are actively working hard to analyze all the data. This is a first kind of sneak peek at the nanoscale features that are present in this material that we were able to demonstrate using our transmission X-ray microscopy technique. And it shows you very nicely the formation of these keyhole pores, nanoscale pores, which have never been observed before, and cracks that form that we were able to observe interplay with the melting process. So with that, I'd like to thank my ever-growing research group. I have, the names of the people who worked on steelmaking in orange, the people who worked on the 3D printing in pink, and thank you to my funding agencies and my collaborators. I'm happy to take questions if there's time.
Have you looked at such processes as they happen, for instance, in stars?
In stars? Yes. We tried that one time. It turns out stars are kind of hard to see. So there are some ways of simulating what a star does using really high energy density plasmas. We do work with plasmas of that type of energy density, but we usually are looking after the plasma at the shock waves that get generated by them. It's a really interesting question, and it's an active area of research. We just haven't explored that one yet.
So my question was regarding the first part of your talk with the metal manufacturing. So I feel like I missed the transition where you talked about sustainability and how your findings have led to improvement of processes, or at least suggestions for that.
So at this point, I've been at Stanford for 2.5 years, and I must confess I have not actually transformed any steelmaking plants. That said, we are working with several companies, including some startup companies, at looking at how we can use fundamental science to be able to either update current processes or design completely new processes that use modern science and technology to be able to rethink the way that we do direct iron reduction. So I would say it's a great question, and one that we are really enthusiastic about answering for you, maybe next year.
Thank you, Leora. Well, it is my great honor to introduce our alumnus speaker. As I said earlier, unfortunately, Craig Barrett couldn't make it, so now I have the somewhat difficult task of replacing Craig Barrett up here. I'll do my best. So Wally got his PhD in 1972 in our department, and when he arrived, there was a new area of material science that was getting interesting, which is the area of semiconductor materials, and that's where he chose to do his PhD. Wally actually comes from an academic family. His father was a famous material science professor. In fact, I still use his book in my phase equilibria class as some of the most beautiful illustrations of surfaces and how they come together to form ternary phase diagrams. They're really these exploded diagrams that are really beautiful. They're almost a work of art. So interestingly, when Wally told his father, he told us this last night, told his father he had the choice between Stanford and Berkeley, his father was disappointed he chose Stanford because he didn't want to hang around with a bunch of scientists, apparently. Berkeley had a bigger reputation for being a serious engineering department, but things seem to have worked out quite well for Wally since. I have to say, personally, Wally has always been a great friend of the department. I remember when I was an assistant professor, we had an external advisory board, and Wally would come and be really generous with his advice. He led the board energetically and also fundraising for scholarships. And what I always find really impressive and refreshing about Wally is that you learn about his career. And his career has taken him maybe a little bit far from fundamental material science, but he will be very happy to have a conversation any day about point defects in 3-5 semiconductors, precipitate clusters, magnesium doping in semiconductors. So it's really great that he keeps this passion for fundamental material science alive. So without further ado, it's my honor to invite Walden Rhines to the podium.
Well, thank you, Alberto. It was my pleasure the last time I was here to do the introduction for our honoree, Bill Nix. And at that time, I highlighted many of the firsts he had established in the world, in the university, and a distinguished career. But I also highlighted a first that few people knew about, which I discovered reading his autobiography, and that is that he believes that he had the worst undergraduate grade point average of anyone ever admitted to the College of Engineering, a record which may still stand. So this past year, I've kept my eyes out for other further distinctions, and you'll be glad to know I found one, yes. I was reading the biography of Elon Musk, written by Walter Isaacson, very well-known bestseller. And there I have reproduced here exact quotes from the book. It said that Musk planned to enroll at Stanford at the end of the summer to study material science as a graduate student. But as he got closer to enrolling, he began to worry. I need to catch the internet wave. So he actually hedged his bets, and he officially enrolled at Stanford and then immediately requested a deferral. Well, what he said was, I've written some software with first internet maps and Yellow Pages directory. He told Bill Nix, and the material science professor. Now, I would probably fail, and if so, I would like to come back. Now, we look to our professors not just for guidance on our research and for technology, but also for career guidance. And so, Elon, approaching Bill, got some good career guidance. Bill said, if you delay your material science PhD, you will likely lose that opportunity forever. He said, we'll defer you, but it'll be a mistake. And indeed, Elon Musk had to go through life without a PhD in material science. Just think how successful the guy could have been if he just followed Bill's advice. Well. So I did follow Bill's advice, and I'm going to tell you some about it today, because Alberto asked me to. And let me start with some of the distinguished people I got to know here at Stanford, starting with my principal advisor, Dave Stevenson, who was a Renaissance man and interested in almost everything you could come up with. He taught thermodynamics and electronic materials, point defects, but he was also an incredible jock. Ski patrol, mountain climbing, 5 times to the international finals for Ironman. He won 3 times, and one of those times, they didn't have anyone else in the over 60 category, so he ran with the 55-year-olds, and he still won. What a guy. And then there was Craig Barrett, who unfortunately isn't here today. I'll show you in a minute why that might be fortunate. But anyways, when David Matlock and I arrived here at Stanford in 1968, Craig had just come back from his postdoc in England, and he taught the Introduction to Materials course, which we took. And for me, it was a great benefit that I had Craig on my committee, because he was an expert in electron microscopy, and I needed that. And many times, well, not many times, but sometimes I've highlighted in speeches, here's Craig Barrett, high temperature creep, his whole career, dislocations, all this kind of thing, and yet he made a change, and I was his first electronics thesis. Craig has corrected me. He said he had a student 4 years earlier who did mechanical properties of silicon, tensile bars and stuff like that. Craig, come on, you call that an electronics thesis? Anyway, Craig had another attribute that made him quite valuable, and that was that he would willingly pay for beer at the O, along with Marsh Pound and John Hurth, and we took full advantage of that. Now, about 7 or 8 years ago, I received an award, and so I invited Craig to do the introduction, probably similar to what he would have done today, because they still talk about it. Apparently, there was not a clear understanding. He was supposed to introduce me as an honor, and instead they referred to it as the greatest roast they have ever had. Leading off with, Wally was the person we least likely expected to ever receive an award for anything. So there are some benefits that his flight was canceled and he was unable to get here today. At any rate, he had a very close connection with our honoree, Bill Nix. And one of the things that connected them was the book, Principles of Engineering Materials. Barrett, Tettleman, and Nix. Alan Tettleman unfortunately died in a plane crash in San Diego. But at the time David and I entered the class, the book had not yet appeared in hardcover, so Craig got us mimeographed copies, and he charged us each $10 a copy. I thought fairly reasonable to get the mimeographed version. Now, what I have found since then in researching this talk is that Craig and Bill have since been trying to catch up with Elon Musk by jacking up the price of the book. Today, it sells for $244, and not only that, it's sold out. So, congratulations, Bill. Great accomplishment. So, what about the other members of my committee? Well, a very special one, Gerald Pearson. Now, he was one of the group that Frederick Terman recruited to come to Stanford from Bell Labs because he had worked on the transistor. In fact, he was one of a small circle of 5. Bertain, Bardeen, and Shockley got the Nobel Prize. He did not. But Gerald Pearson got the original patent on the silicon solar cell, a very accomplished guy. Now, if you went into his office, the unfortunate part was he continuously smoked cigars the entire day, so you could barely breathe. But I made it through that, and Gerald introduced me to one of his former graduate students. So Mole, Spicer, and Pearson were the advisors for Morris Chang, who had moved on and was head of the semiconductor business at TI, later founder of Taiwan Semiconductor and UMC, TSMC, now the largest silicon foundry in the world. And so Gerald introduced me to Morris, who created a job at TI, and then became a friend for life, which was a real benefit. And then there were the students. One in particular I want to highlight, Herb Maruska. Unfortunately died a few years ago, but he had been working at RCA and came here on an RCA fellowship, and RCA was desperate to develop a blue light-emitting diode. We had pretty good red and green, but no blue. You couldn't create white light. You couldn't do the full spectrum. And so Herb was trying, and for the first 2 years, really made no progress, even though he brought gallium nitride technology, deposition technology with him. So one day, Herb and I sat down and just spent the day going through the periodic table and looking, and for each one we looked up, has anyone done this? And we came across magnesium. No one had ever tried magnesium. Herb went into the lab. He tried magnesium and gallium nitride. It created blue light, and history changed a little. So Herb did his thesis on the blue LED, and then some years later, the Nobel Prize is awarded for the creation and optimization of the blue LED. Nakamura, Amano, and Asaki were the 3 winners, not Herb, strangely. And when that was announced, we found out that if you win a Nobel Prize, you are a Nobel laureate forever. It can't be taken back. It can't be changed. You can be a child molester, whatever. You're still a Nobel laureate forever. And the things that are said about what you accomplished cannot be changed. We offered to have some things corrected where they actually claimed developments that Herb had already done. But at least Nakamura, in his speech talking about it, said, "I do not think my or Akasaki or Amano's work would have been possible without Maruska's contributions many years prior." So he acknowledged the importance of that. Now, I, of course, was in communication with Herb after the announcement, and I didn't have a chance to take a picture, but I thought if I had taken a picture of Herb's reaction to the awarding of the Nobel Prize to people other than himself, it might have looked something like this. Now, that's Bruce Liebert. You see, he's right out here in the audience, and obviously the more serious of the 2 people in graduate school. Well, Herb and I, along with Dave Stevenson, applied for and received a patent. It was 1974. It patented the use of magnesium as a dopant in gallium nitride to produce blue light, and Stanford owned the patent. Wow, great for Stanford, don't you think? Total royalties, $0. Unfortunately, it didn't become commercial till long after the 17-year period. But when the Nobel Prize was announced, Herb was a little incensed, so Herb and I got together and we wrote a paper that was published in Solid State Electronics where we tried to be as polite as possible and give some credit to others. Clearly, Nakamura was the principal inventor, invented the quantum well structure and modulated the band gap with some indium. But Akasaki and Amano had visited Herb at RCA and then gone back and reproduced his results. And the best we could do is say, well, they got a little better purity, a few less dislocations, and so they got it. But in the article, we try to politely explain what Herb did, and really for the department, I think you can be proud you had yet another who should have won the Nobel Prize. And then there was Shang Yishang. Now we're all up at 207 McCullough. Herb and I had the office in 207, and across the hall was the 3.5 lab, and then down the hall was the 2.6 lab with all those things like selenium and tellurium that build up in your body in parts per billion over a lifetime, and I'm expecting to feel the effects sometime in the future. But Shang Yi was working with gallium arsenide. He had two advisors, Gerald Pearson and Dave Stevenson, and Gerald recommended him as well to Morris Chang. We both went to TI, but he stayed with Morris Chang and ultimately became the senior vice president in charge of R&D. If you're wondering, how did TSMC go from a tight race with Samsung and Global Foundries and become the dominant silicon foundry? How did they leapfrog ahead of Intel and become the leader in process development? That was all Shang Yishang as head of development. He moved them into extreme UV, well ahead of Intel and other competitors. A major achievement. He's retired now, lives in the Bay Area. Okay, so we went to Texas Instruments, and TI was in a state of desperation. I found in my career this is useful. The best innovation comes when you're desperate. And in this case, charge-coupled devices were the new thing to build solid-state imagers and memories and other things. But unfortunately, Fairchild, Sony, RCA were all well ahead of TI. So they had to come up with something different. So what we did was, instead of shining the image on the front side where the device structure was, we developed a process to thin the silicon afterwards to about 20 microns thickness, so you could shine the image on the backside, you generate electron hole pairs, you collect them, and CCD, you clock them out, and you have a digitized image. And it turned out that the military, with its starlight scopes, wanted to not have to have the photons come in through all the device structure. So we managed to sell a bunch of contracts and do the first paper on thin backside illuminated CCDs. Unfortunately, this is another one where it was 25 years later that it was adopted in industry. If you take apart your cell phone, you'll find it has a backside illuminated imager, but in fact, they didn't until about the year 2000. We sort of ran out of welcome at the Department of Defense in the night vision lab because we had demonstrated it, it worked, and they said, hey, no more contracts. Dean Collins, the head of the group, comes back. There are only about 6 or 7 of us, and says, hey, we're not going to sell any more contracts. What they want to do now are heads-up displays for jet pilots. So, oh my gosh, display technology. Here we're good at imaging. What do we do? And Larry Hornbeck, one of the guys in the group, very innovative, said, when we thin these things, the silicon, what if we thin them into little mirrors that are attached with torsion bars, and we could make a light modulator. You could shine the light on, and then you could turn them on and off, and make a heads-up display. And we did. Larry did a 3x3, and it grew over time, and it ultimately became what TI referred to as the digital light processor. It was adopted a variety of places, but the one you have been exposed to most is if you go to a movie theater, they used to send film around, acetate film, when they put out a movie. Nowadays, they send it out electronically in compressed digital video. And in fact, all the theaters in the world use this device to do the projection that you see. And Larry got an Academy Award based on the etching process and on the device structure that was developed and that was adopted today. Well, once again, desperation. But in my case, I began moving more and more from materials and more got involved in designing chips. And TI had a consumer products group that was growing very rapidly. So rapidly that there was nowhere in Dallas to accommodate them. So they did a really bright move. They moved the group to Lubbock, Texas. Very few people wanted to move to Lubbock, Texas. And so it's the only reason a 28-year-old could become the head of engineering for a rapidly growing group. So that's what I did. And we were doing mostly calculators then. Now, TI not only sold components for calculators, but also sold the calculators themselves. The early ones up to 500 components, they're shown on the left. And by the time I got there, they were down to about 50 components. And they had one of these big, hairy goals, like putting a man on the moon. Let's do a single chip calculator. So that was the focus. And in fact, we did. We later did a single chip scientific calculator. And you're probably wondering, how much money did TI make from all these innovative developments? Not very much. The fact is that we had Japanese competitors who were great optimizers, and so they followed quickly. And so our consumer calculators, add, subtract, multiply, divide, were losing a lot of money. So much money, in fact, that we decided that the best way to lose less money was to simply have the Japanese produce the calculators and then put our name on them. You can see the similarity. That Toshiba calculator and the one on the right has a little TI logo. And that way we lost less money, but it really wasn't a very good business. And we were looking for other ways to make it a good business. Now, we had one product that had a life of its own. It was called the Little Professor, and it would flash up an arithmetic problem, 2 + 2 =, and the student could enter a number, and it would tell you if you were right or wrong. And we kept thinking it would go away, but every year it stayed and it grew, and we convinced ourselves it's because parents will do anything to help their kids in school. So Paul Breedlove, who was in the group, he's the third one from the left, got this idea, why don't we teach spelling? Well, to teach spelling, you've got to say words and let people spell them. But once again, a period of great desperation. We're losing money, so why not? And so they came to my group, the engineering group, to develop a chip. Larry Branningham's the one on the right who designed the chip. But it was a strange situation because the consumer products group was independent from the semiconductor group, and we were in a pricing war with Morris Chang, who ran semiconductors. You know, we were always looking for lower prices because consumer products have to be cheap. And Morris finally got tired of fighting it, and he said, hey, $2 a wafer, that's it, no more negotiation. This is a 2-inch wafer. $2 sounds a little low, but anyway, so we had to do it in P-channel MOS, the oldest, the slowest, the most archaic technology. And here speech processing is very computationally intense. It needs the highest performance. It needed N-channel MOS, but Larry didn't know how to design with anything but P-channel MOS anyway, so he did a pipeline multiplier in P-channel MOS, actually produced speech. We introduced it actually with a lot of opposition because the management thought that any consumer products over $40 required the permission of both parents, and you'll never sell it at $60, but we did, and then we raised the price. So we managed to diversify the business so much that a decision was made to redirect the whole business to just focusing on the education market. That's, in fact, exactly what the company did. And they then moved into a wave where they provided courseware for grade school, high school, junior high school, and they sent teachers to Las Vegas for rewards and for training and so on. And pretty soon it was all education. Now that's a TI-89 titanium calculator, and it sells for $150. Now, I personally, having raised 2 daughters through grade school, junior high school, and college, have purchased 8 of these calculators. They lose them, they need different ones for different courses, they lend them to friends. And knowing full well that TI was paying a Chinese subcontractor $20 a piece for these calculators, it became a gravy train of money. And as a result, the Consumer Products Group, which had been losing a ton of money, started making money. And I have here, by the time they got to the year 2000, they were up to 50% gross margin. It continued to increase steadily. By 2007, it was at 65%. And at that point, Texas Instruments decided to stop reporting consumer products as a separate entity. Now, I don't know exactly why, but let me speculate, since I was a senior manager there. I believe the reason they stopped reporting was that the numbers became embarrassingly good. They were making far less than that with their semiconductor business, so why tell everyone you've got a $1 billion consumer products business that's generating 65% or greater? And so they now hide the numbers, but it's still a great business. Well, here I'm back and forth to semiconductors, consumer products, and so heading to the semiconductor group again, we had another sort of disaster situation. In 1978, I'm still in Lubbock, Texas, trying to figure out how to get out of Lubbock, Texas. And Intel introduces the 8086 microprocessor and, in April of that year. And the TI had one also called the 9900. And then Motorola announced the 68000 and Zilog the Z8000. Now, when I joined TI, over on the left side, TI had come to dominate TTL. That made them the largest semiconductor company in the world. TI, Motorola, Fairchild, the big three, but TI the leader. But MOS came along, MOS memories, MOS microprocessors, so things were fading. And so the 16-bit microprocessor was a turning point. And this group in Boca Raton had been set up by IBM called the Entry Systems Division, and they had been told, go do whatever you want to develop a consumer personal computer. But John Opel, the CEO, had a requirement. He didn't want them to damage the IBM name, so they had to go through an IBM qualification of their product. Well, if you haven't been through an IBM qual, that means thousands of production parts with a stable process. And unfortunately, the Motorola 68000 was not that far along, even though it was by far the choice of that group. It was a big Indian, referring to byte order, whereas Intel was a small Indian. It was a 24-bit architecture that could go to 32, had 24 bits of logical address space. Intel had only 20. And then there was TI with 16 bits of logical address space. It turned out Intel and TI were the only two who could pass a qual. So then the decision came down between the two of us. And many years later, IEEE Spectrum, who discovered the actual evolution, asked me to write an article. Now, I did not name, did not name the article. They reworded it to say the inside story of Texas Instruments' biggest blunder. Didn't really feel good about that. But anyway, told the story of how it came down to Intel and TI. Now, the interesting part is TI, when they figured out what a dog the 9900 was, it didn't have any peripheral chips, so we put an 8-bit bus on it so it could use 8-bit peripherals. Really smart move. So now it ran at exactly half the speed, 2 cycles to take in data and take it out. That was even worse. We called it the 9980. That was even worse. Jack Karsten was head of the group. Jack leaves TI. He goes to Intel, and surprise of surprises, the Intel 8086 now has another version called the Intel 8088 with an 8-bit bus. It's an even worse dog. And so we have the two great dogs of the industry, the 9980 and the Intel 8088. And so this mysterious division in Boca Raton comes along. They want to buy something really cheap. Andy Grove says, not on your life, I'm not selling the 8086. And then he says, well, we've got this dog, the 8088, that nobody has bought. Why don't you offer them that at the price they want? And IBM took it. That is why you today struggle with your PCs, because the Intel 88 was, in fact, the chip that they designed in. The one thing I can say is, even though it was one of the worst computer architectures ever created, the 9900 was actually worse. So So what do we do? Oh my gosh, I'm head of the microprocessor division. I'm actually a vice president now, and everyone's looking at me, so we say, look, host microprocessors were the big thing today. Maybe special purpose microprocessors will be the big thing in the future. So we designed 4 of them, one for communications, one for graphics, one for mass storage, and one for local area networks. It turns out the first one, the TMS-320, a digital signal processor, ended up being the big winner by far. In fact, ultimately, it and its derivatives was more than half of TI's total revenue, so a big success. But a lot of illogical things. Now remember, we're in a state of true desperation. That's the time you have great innovations. And so when we introduced it, the things I've heard in courses on strategy is the most important thing to get a winning product is be first to market. And the second most important thing is be first to market, and so on. Well, we weren't first to market. In fact, there were 7 companies or 5 companies that got there ahead. But the TMS-320 actually was pretty well defined. Now, it was defined because we thought we knew what the end markets would be for a digital signal processor. We had done speak and spell, so we thought it would be very speech-oriented. So we identified those markets and designed it so it did those things very well. And that's where I learned a very important lesson. If you introduce innovative technology, you cannot predict what people will use it for. You have to let your customers predict. But of course, marketing managers don't like that. They want to have a clearly defined target market. So those are the planned targets: speech recognition, speech synthesis, and so on. The only one that ever saw appreciable revenue for the TMS-320 was modems. The actual ones all came from businesses that didn't exist when we designed it. So disk drives were moving from analog to increase the density. They had to go digital. They all designed it in. Cell phones were going from analog to digital, and so TI got 55% market share in cellular baseband, and really only in recent years turned that over to Qualcomm, and a variety of other applications. So a big success. Other lessons here. We should actually have known this would happen because we had already demonstrated it before. We just didn't remember it. And that's with a device called the TMS-1000. It was a 4-bit microcontroller. Here you see it. You can barely see down in the right that 375. That means it was announced on March 1975. And look at all those wonderful applications: data terminals, electronic cash registers, flow monitors, so on. As nearly as I can tell, there was never a nickel of revenue generated by any one of those applications. And because it was a $5 part, its principal attribute was it was cheap. Not cheap enough. So here we saw the sales force beginning to innovate. They kept discounting it again and again till we got down below $2, and all of a sudden a new market emerges whose principal requirement is cheap. That market, electronic toys and games, generated over $100 million per year for the TMS-1000 for the next 5 years. Didn't exist when we designed it, never could have predicted it. And there's another lesson too. It's the lesson of if you work in large corporations, you hear all this talk, oh, our divisions are very sympathetic, are very synergistic, they help one another, they work well together. I can assure you this is rarely the case. So here we have, it's very difficult to do business with your brother-in-law. You know, there are no rewards. If you're successful, then corporate management is beating on you to lower the price or build more units and so on. So the best thing to do is avoid your sister division. So here we have Motorola, king of communications. Business started on mobile radios and now moving into cell phones. And here's TI, a business based on computing for seismic data analysis. And so what do? So Motorola designs the premier processor for data processing and servers, and TI designs the premier processor for communications. And we all live very happily because we could sell to each other, not to our sister divisions. Okay. On to the data systems group. Believe it or not, TI had $1 billion computer business. It had worked its way down to about $500 million when I took it over. But it was mini computers and portable terminals and printers. Actually a very good business. But once again, here TI in desperation is saying, we're We're an also-ran. We need something to distinguish us. So we had to come up with a new idea. And guess what it was? Artificial intelligence. Why not? It's 1986. Why not build an artificial intelligence computer, software, everything that goes with it? This is a copy of High Technology magazine. That's the cover. You see artificial intelligence. Heavyweights get into the act. Heavyweights meaning TI, as George Hallmeyer with me, who had been head of DARPA, as head of R&D. If you look very closely, you can see my smiling face. You clearly recognize me, I'm sure. So we thought AI was going to take over imminently. After all, it's 1986. Only took about 40 years, but we weren't actually the worst. In 1956, we had a convening of all the experts in artificial intelligence in the Dartmouth Research Project. And at that time, they came out with their projections for the future. One of those, within 10 years, a digital computer will be the world's chess champion. Well, not quite. It was 40 years later, not 10 years. We had Marvin Minsky, who started the AI lab at MIT. He said, from 3 to 8 years, we'll have a machine with the general intelligence of an average human being. Now, I think that says a lot more about the general intelligence of an average human being than it does about AI. And there were many others. In fact, there was a movie in 1968, 2001, A Space Odyssey, where the computer had human-like characteristics. In fact, the members of the crew got in a dispute, and the computer had to kill some crew members, so we couldn't call it IBM, so it shifted one letter left in the alphabet from IBM to HAL. But now we go to the year 2001. Where are the computers? 15 years later, they're not there. And what we have are neural networks that can distinguish between cats and dogs. A bit of a shortfall, I would say. Well, what happened? We didn't have much big data sets to analyze, as you saw today in talking about big data sets and machine learning. We had limited computing power. We needed more advanced algorithms, but mostly there were no killer apps. One by one, these limitations went away, taking us to the present day. And so today, if you look at what makes for success in the semiconductor business today, it's AI, and your value of your stock is determined by how many times you can say the word AI in an average earnings call. Here, I have plotted the major competitors. You can see on the horizontal axis, this is the number of mentions of AI in their most recent earnings report. And on the vertical axis, their 12-month increase in stock price. And here you see it. NVIDIA wins hands down, twice the number of mentions of AI. Clearly, they deserve the highest stock price. Okay, so here I am, a semiconductor guy, and the CEO of the company, my boss, tells me, Wally, if I were you, I would go find another job. It wasn't out of any dislike. It was that he said, look, I got this job late in life. I'm going to be here for another 10 years. You're not going to get a promotion. Why don't you go somewhere else? So he didn't stand in my way. Unfortunately, I had a non-compete agreement, so I had to leave the semiconductor industry. And so I ended up at a company that was very troubled. But I always liked troubled situations. But this one in particular, you can see this is Mentor Graphics. They were one of the big three of electronic design automation. And there you look at about 1990, they peaked. You can see them on the downward trend. Could easily have gone to zero. I joined in 1993, and fortunately, this is always a good thing I recommend. If you take over a responsibility that's doing well, no one ever figures you did anything. But if you take over one like this, people think, wow, what a great contribution, even though it wasn't that stunning, 6% growth. But anyway, the company grew, and EDA, Electronic Design Automation, is an interesting software business because it's actually it's actually very concentrated. The three largest companies have always had very high market share: Computer Vision, Calma, Applicon, Daisy, Mentor, Valid, Mentor, Cadence, Synopsys. Over 75% share, more recently 85% share. So large market share. There are only about 50,000 designers in the world, so price competition is worthless. You lower the price, you just lower the TAM. And so the trick is just increasing your penetration. And the way you can do that is each segment, each specialty in design automation has a leader. The leaders are shown in blue. Those are the ones with #1 market share, Cadence, Synopsys, Mentor. The horizontal axis is the 10 largest segments of the business, like printed circuit board design, analog design, things like that. And on average, the #1 has a 72% market share and a minimum of 40% market share. Very easy to make a lot of money in a business where you have 70% of the market. And that, in fact, is what happens today. Very good investments in EDA. And so things were looking pretty good. But when you run a public company for 25 years, bad things are bound to happen. And they did. So whenever your stock price goes down, people show up who want to take advantage of the situation. Cadence came after us with an unfriendly takeover attempt in 2009, which was stymied because they couldn't get financing. But Carl Icahn got the word and said, oh, Wally is just trying to keep his job. I'm sure that Mentor should be sold. So Carl came after us, proxy contest. He wins the proxy contest, gets 3 directors. And that Christmas, on the left side, you see the bottle of scotch Carl sent to me. It says, "Not for use at board meetings!" ! Cheers, Carl. So I had to deal with a mixed board for a year or two, but then Carl finds that his stock has nearly tripled, and so Carl sells out, not without a lot of personal conversations and criticism, but anyway, he sells out, makes a lot of money, and the bottle of scotch there came Christmas the year after he cashed out. It says, "To be used at board meetings." Cheers, Carl. Okay, so we're home free in 2010, and then 6 years later, along comes Elliott Associates, one of the most aggressive of the private equity companies. They want to do a going private transaction. There is no way to escape. So fortunately, one of our directors had a close relationship with the CEO of Siemens, Joe Kaeser, and so we brought them in as a white knight, sold the company for $4.5 billion, and then it turns out they wanted a smooth transition. So they asked me to be, quote, CEO emeritus. Now, let me tell you, if you're ever offered the job of CEO emeritus, take it. It's great. You get paid, you give speeches, you meet with customers. Unfortunately, I knew this gravy train would only last a certain while. Actually, it lasted for close to 3 years. So I went off and did other things. And the people at DARPA asked me to work on accelerating the transition of technology to the market. They thought they had great inventions, but they were very slow to be adopted. So I did that. And one of the projects they asked me to look into was homomorphic encryption. If you haven't heard of it, fully homomorphic encryption was invented several hundred yards from here by a graduate student, Craig Gentry, in his PhD thesis. He was working for Dan Bona. And it's one of the truly remarkable achievements in recent history. This was 1989. And the reason it's so significant is it's going to revolutionize information sharing. We generate quintillions of bytes of data per day, but the people who own the data are reluctant to let others use it because they'll just copy it, and how do you get the value again and again? And the answer is you keep it encrypted and you never expose the plain text data. Well, that's sort of strange. You send your data to a computer center, even if it's encrypted, they're going to decrypt it, do the computation, and then re-encrypt it. So, somehow you've got to give away the key. But fully homomorphic encryption is different. You, the client, encrypt it in a very secure form of encryption. You send it to the cloud. In the cloud, they perform the computation on the data while it remains encrypted. No one else has a key. It remains your data. They send back the encrypted results. Pretty revolutionary. One minor problem. It is computationally unbelievable. So here's what it does. It takes a single bit of data and converts it into a 500-OR polynomial with 64-bit floating point coefficients. And in the end, you take 4 bytes of plain text data, and in encrypted form, it goes to 1.7 megabytes. You do a single CPU operation, compare that on plain text. It requires 12 million CPU operations, plus there's a lot of overhead. So plain text computing that can be done in 1 second takes 11 days. A bit of a challenge, but nothing for fast movers. It turns out that people have been making improvements right along since it was developed, mostly with software. But the next step is going to be software and hardware. And multi-core computers are the way we speed things up, but traditional computers won't do it. The data movement problem is so awesome that you can't do it on a von Neumann computer like an Intel or an NVIDIA computer. What happens is you use more and more cores, up to 4 or 5 cores, the computation improves, and then the overhead of shared memory and synchronization overwhelms it, and it gets worse. What you need is a custom reconfigurable architecture. You need to be able to create extremely wide words for parallel processing, 10,000 bits or more. Well, NVIDIA uses one form of parallelism, single instruction, multiple data. Intel uses a different form, but in fact, there are 55 forms of parallelism identified by Patterson and Hennessy. And if you can have a processor that uses all of them, deep pipelines, massive scalability, and is programmable, then you can solve the problem. And that is what a company with thousands of compute cores per chip called Cornami, which stands for a tsunami of cores, has been able to do. And so that's been my job for the last 4 or 5 years as CEO of the company. What can you do? Banks would love to investigate money fraud, money laundering, and all that, but they can't share proprietary data. But if they encrypt it with fully homomorphic encryption, then they can share it with others and analyze transactions, and they plan to do so. You have applications like medical diagnostics. Who would trust a doctor to analyze your MRI or your X-ray? Computers are so much better, and they build as the database gets bigger and bigger, but nobody wants to give their medical data. But what if your doctor encrypted it on the spot? No one could ever see it again. It was in a form of encryption that was highly secure. Then you might be willing to. In fact, even China might be willing to share their 1.4 billion patients' data with us so we could build really big foundation models for medical diagnostics. You can build machine learning models from encrypted data. And so you can do encrypted queries to an encrypted model, get encrypted results, all without ever exposing the primary data. So a new data revolution. And there are other things too. What semiconductor company would ever let the equipment manufacturers see their sensor data? Because that's the way all new processes get ripped off. But if you encrypted it at the sensor, then they could do all sorts of yield improvement, predictive analysis, and energy efficiency, and so on. So this will be the next revolution. And it has some other benefits. Big fines in Europe with GDPR regulations if you expose your data. Meta is looking at a $1.2 billion fine, other companies. But if you use fully homomorphic encryption, you are GDPR clean. You are not subject to those regulations because your data is never exposed. And there's another benefit. Sort of the impending doom from the sword of Damocles. When quantum computers get beyond 10,000 qubits, then they will be able to break most of the security in the internet today, except for lattice-based encryption, which is what fully homomorphic encryption is. So it inevitably offers the future for us, regardless of all these other uses. So that's my current role, but you just can't get away from this material science thing. So today, after spending those 4 years working in gallium arsenide and gallium nitride in the McCullough building, I'm now chairman of the board of a company that does nothing but gallium arsenide, gallium nitride, $4 billion in RF components. I've been on the board for 29 years. And if you want to get more materials oriented, I'm on the board of a company called Pallidus, which actually grows silicon carbide. A material science guy, once again, and I look just about the same as I did when I was in grad school. Thank you.
Wow, what an amazing talk Wally just gave. I learned so much from your talk about department history. And the current graduate school life is as fun as before, we guarantee. Now let's come to our keynote presentation. I'm Yi Chui, a faculty member in material science. I joined the faculty in 2005. Before I introduce our keynote speaker, Steve Chu, let me also share just a little bit of my interaction with Bill Nix. I cannot go without saying school dislocation as well. So I remember more than a decade ago, my lab saw something, a nanowire, grow and straight, but with the branch, epitaxial branch coming out. This is lead selenide, lead telluride, lead sulfide system. We couldn't understand why this branch is rotated. Well, it turned out to be, after talking to Bill Nix, he said, do you know about Ashby twist? I have no idea what Ashby twist is. We started to look into this. That was a great fun of collaboration since. And with school dislocation in the middle of the nanowires, it caused a twisting of the lattice, caused this spiral behavior. Not only Bill Nix was excited about this, also David Barnett joined the team as well. Through this process, I see that as a coaching process for me as a junior faculty, how senior faculty will work. Graduate students, you probably don't know how our professor will work. I remember the night, 3 of us email back and forth. We didn't have use social media yet. And Bill and David was driving this school dislocation, Ashby twist equation, checking back and forth. I think we worked from roughly about 7 p.m. until roughly midnight. Then we say, oh, we all need to go to bed. And that resulted in a very exciting publication in Nature Nanotechnology. That was a feature cover. And so over about a decade long, Bill and I collaborate together on silicon anode batteries, the mechanical property of that. I just learned so much about mechanics from Bill, as well as Rainer Dauskas and others. I was trained as a chemist. That was my complete exposure to mechanical property of materials. So thank you, Bill, for coaching me over the years. Now let me move to Steve Chu. Steve, hopefully your slides are ready now. I can go longer, so you can have maybe 5 more minutes to prepare the slides. Another amazing person. So Steve, so official introduction is Nobel Prize winner in physics due to the laser cooling, Secretary of Energy during Obama administration. Many, many titles, awards, I won't go through. But let me share with you my own version of introduction of Steve. 3 things. First is Steve is a person who utilizes all the opportunity to influence people around him to do the right things. That's super important. We know you could be an excellent scientist, but you probably would not go one step further to influence people around you. But Steve is the type of person. So when I was a postdoc at Berkeley back in 2004, 2005, I joined the Stanford faculty coming over. It was through Steve's influence, I decided, after coming to Stanford as a faculty, instead of working on my nanoelectronics and biosensor research, I said I would be willing to do a 20-year detour to work on clean energy. but I didn't know much about clean energy. I appreciate material science department has been so flexible for me to do whatever I want. That's how I get into battery research. So that's the thing about Steve. The second one is the degree of dedication he has is just incredible. I told you about interaction with Bill Nix. We work until midnight. Let me tell you a story about Steve. So one night, about 9 p.m., after he already come back to Stanford from Secretary of Energy, I received a phone call from Steve about 9 p.m. He said, I have a great idea. Let's discuss about this. After about 10 minutes, I heard somebody yell at Steve on the other side of the phone and say, Steve Chu, you need to come in now. I said, Steve, what happened? Steve said, oh, I fell from my bike. I broke my collarbone, emergency room. I said, I'm now ready to go into emergency room. That's Steve Chu. This is for graduate students to listen. That's the dedication you will need to get things going. The third one, I also learned from interaction with Steve about his speed of learning about a new topic. He's never afraid of learning about new things. He will come to a topic, maybe knowing very little about this and having a discussion with you. Then the second day, he will make a meeting with you again. Then you find out, you say, overnight, Steve Chu just learned so much already. And then third day, you're going to have another meeting with him. Within about a week, he will get to the top of the understanding all the issue around that topical areas. So that's fast learning, self-teaching, searching online, talking to people. That ability, I think really will be very, very important for everybody to know about. It influenced me when I do research. So I enjoy the most of my brainstorming with Steve. We used to have once every 2 weeks before COVID, the brainstorming. That was very, very effective. With that, Steve, I hope your slide is ready. Now the floor is yours. Please, let's welcome Steve.
Well, Yi, that was an amazing introduction. I didn't recognize the person you were talking about, but thank you anyway. So anyway, I'm delighted to be here to be part of the Bill Nix Lectures. Truly, this is a great material scientist whom you will hear a lot more later, or if not. But I want to talk a little bit about the role of materials in how you meet our greenhouse gas challenges. So what's the challenge? The challenge is, since the beginning of the Industrial Revolution, the temperature of the Earth has been going up. Here you see approximately a rise of about 1.2 degrees centigrade, and we believe this is due to the emission of greenhouse gases. What you see here is the brown curve. The black is measurement. The brown is a compendium of many computer simulations of climate. And then the blue is simulations where you decrease the amount of CO2, you take out the CO2 emitted by humans since the Industrial Revolution. It's not only CO2, but there are other significant greenhouse gases. Methane and molecule for molecules about 84 times worse, but it has roughly a 10-year lifetime before it becomes CO2. Nitrous oxide, N2O, is about 300 times worse and lasts hundreds of years. And so these are significant greenhouse gases. Where are we on the overall scheme of things? These are various scenarios of how we will begin to keep our planet from increasing above 1.5 or 2 degrees. But you see here on the x-axis is time, 1900 to 2100, 1990 to 2100, and on the y-axis, carbon dioxide emissions equivalent, which includes the methane, N2O, and other gases. So we're the red dot. We're somewhere between no climate policies and current policies, essentially going in the same trajectory. There was a little dip in COVID, but we've recovered from that. In order to stay below 2 degrees, you see that the overall greenhouse gas emissions has to go to 0. That's 0 of everything, and that is very, very difficult. So let me say that there have been unintended consequences of multiple industrial and agricultural revolutions, but I want to take you through some of them and show how materials developments have been crucial to that. And so I will start with a well-known quote that says, "Those who cannot remember the past are condemned to repeat it." I prefer the Gan Wilson cartoon, which says, "You will make the same foolish mistakes you have made before, not only once, but many, many, many times again." And so you will see a little bit of that in this talk. All right, the Industrial Revolution. James Watt improved the Newcomb's steam engine, and it was that improved engine that was really transformed this transition from power from humans and horses and other animals to horsepower. Another great event in the Industrial Revolution was the ability to actually make steel. This was Henry Bessemer and the Bessemer process. And what happened is during the Crimean War, the first Crimean War, where Europe was against Russia, England found it needed stronger materials to replace the cast iron cannon barrels because the new explosive force would break the barrels. And so he invented this steel process. So it's the ability to make iron and then steel in large quantities economically, which really powered the Industrial Revolution. Another revolution was the revolution in computation and telecommunications. We all know of Bardeen and Bertin's first point contact transistor in December of 1947. Shockley's name is not on the patent for the transistor, but Shockley, who was their department head, got so irritated by this fact that 2 of his members did something behind his back. He called them into his office and said, "You know, sometimes people who did the work won't get the credit." And so what did he do? He holed himself shortly thereafter in a room. Shockley was brilliant physicist, and in a couple of days spelled out all the basic physics of semiconductor electronics. And in that, he also proposed p-n junction. He did the p-n junction theory and proposed a much more practical transistor, which was finally realized by Gordon Thiel, Morgan Sparks in 1951. So this part we know, but I want to emphasize that it was the ability to grow germanium and then silicon at an extremely high purity that actually led the way to the transistor. Without that, there would be no semiconductor industry. And so, again, this was Bell Labs people, Bill Fan and Zone Refining, and Thiel and Sparks, who used the Tchaikovsky method to grow the very large single billets of silicon and germanium. So it was this ability to grow these materials that really led the way and allowed semiconductor industry to grow. Should also point out that in optical communications, it was the ability to make very high purity silicon dioxide optical fibers that led us to the optical communication revolution. Okay, so this is a glimpse at some of the materials that allowed these industrial revolutions to occur. But where are we now? And I'm going to talk about what we have to do. So this is a summary from the IPCC's latest summary of where the greenhouse gas emissions are coming from. You see that, for example, forestry and agriculture, over 20%, buildings industry, heat, things like that. Okay, so let's go into some of the challenges and what's happening. For example, in solar energy, we've seen really great progress. This is a cost curve from 2010 to 2019, and there was a huge drop in the price of solar. And even going before that, there's been overall about a 98% drop in the cost of solar modules. Offshore wind, onshore wind, these also have been going on. And the question is it going to plateau? And the answer is, I really don't know, because there's a new kid on the block over the last 10, 15 years, 20 years, and these are so-called new, very complex materials called perovskites. And here you see, as a function of time from 1990 to 2022, you have various versions of solar cells, but these perovskites in red have a much more rapid development recently. And the amazing thing about these things is they're direct band gap. The essential materials are not that expensive, and there really is a hope that you can deposit these materials in thin films, and in fact, by using different perovskite mixtures, you can make a couple of tandem layers in one fell swoop. So this has started, but the whole issue of, they weren't lasting very long, months, weeks, maybe up to a fraction of a year, but very recently, there has been breakthroughs of at least 2 groups I know about where they've been able to stabilize the migration of defects in these materials. And now through accelerated life testing, they're estimated over 15 years of lifetime. When you get to 20 plus years, because they're so much cheaper to handle and make and use less energy than silicon, the hope is that these perovskites will really take over. But never count silicon out is the standard story of everything. But, so we have solar. It's become very, very inexpensive. But this is a map of the solar resources around the world, and although it looks pretty good, you still, if, for example, you live in Northern Europe, you're not going to get much sun. And, for example, if I zoom in on Europe compared to Northern Africa, you see that you've got fantastic solar in very inexpensive land in Northern Africa and deserts, but you have a big market over here. So the object is you're now going to long-distance transmission lines. But let's talk about transmission lines and what they were doing. Way back in the beginning of another industrial revolution, the introduction of electrification, electricity, widespread dispersion of electricity, starting with a Pearl Street station, New York power station with Thomas Edison. The power was made locally. They had a coal furnace to generate steam to make the power, and distributed locally. There was a big fight that eventually emerged between whether you wanted to distribute the electricity in the form of DC, which Edison favored, or AC, which Tesla favored. With AC, you can boost up the voltage to high voltages using transformers, and you can transmit across the city much more efficiently. So there was a real AC-DC war, and Edison actually, to demonstrate that AC was inferior, he took an AC current, and I think the story goes he electrified an elephant. And sadly, this was, he worked in New Jersey, and New York decided this was a good way to electrocute people. So, first application of AC. Anyway, so there was a DC-AC fight, but now let's fast forward, and you're now thinking of transmitting electricity over not tens of miles, but even thousands of miles. And this is a picture of a high voltage transmission line built in China. It's a DC line, 1.1 million volts, and these little things over here on the wires are people. It's a big, big transmission line. This is the high voltage standoff. And so why is it going DC? Because to transmit high power DC, you don't have radiative coupling to the ground, you don't have radiation losses, and so it's much cheaper to transmit in DC. So what do you do? How do you get it from, remember AC is what you use to step up the voltage, and so what people use is they use very high frequency converters to make an AC that then steps the voltage up to the very high voltages. This is a 1.1 megavolt transformer. Those are people down there. Okay, so let's talk more about transmission lines and materials. They don't use copper in the highest voltage transmission lines. They use aluminum. And annealed aluminum is best. It has the highest conductivity. And you have, in this annealed aluminum, you have a carbon fiber to give it the strength so you can string these lines in the high voltage cables. So that's what we use today. And if you step back and look at all the materials we use in the world, it turns out that aside from concrete over here, and maybe asphalt and cement, the other materials we use in large volumes in terms of weight are oil, coal, natural gas, and steel. Okay, and the rest, this is an logarithmic scale, so each dashed line is a power of 10. And so these are the things that we mostly use, and there are a number of people, including Matteo Pasquale at Rice University, who are trying to work on developing replacements for copper. Why does he want to replace copper? Well, first, I showed you that picture of aluminum and copper in these high voltage cables. We're also finding out that you want to go to higher voltage for electric vehicles, so you use less copper because the loss is voltage squared divided by the resistance. And so what Pasquale has done is he's taken methane and converted it into carbon fibers, and he's finding in terms of the strength of steel compared to carbon fiber is better. The conductivity is about a factor of 8 below that of copper and aluminum, but it's gaining. And this is progress only over the last 7 or 8 years. Now the question is, what are the limits to carbon conductivity? And the limits are, it can go at least an order of magnitude higher than copper if you can make carbon nanotubes and link them together to be conductive. Why do we care? Because we are going to face a copper shortage. As we do increased electrification, this is really going to be pressure. And for that reason, as I mentioned before, the EVs are going to first 400 to 600 to 1200 volts to decrease the amount of copper in the car. Now, in order to do that, they had to go to different electronics, so-called power electronics. And to go to higher voltages, you want to use wider bandgap materials other than silicon. The favorite now is silicon carbide. And with these wide bandgap semiconductor materials, you get much better conversion AC to DC. You get higher voltage and frequency ratings. Many, many things improve with these. And so when I was Secretary of Energy, we actually decided that this is something that the US government should invest in to actually figure out how to make these wide bandgap semiconductor materials more cheaply with higher yield that can be used in power electronics. Because the companies who use the materials won't want to do the materials research. And so that's one of the things that we did support. And this, during the time I was Secretary of Energy, I was bragging about investments that led to a very high power silicon carbide power module. This little thing about this big can work at 1200 volts and 880 amps a megawatt. And so those are some of the things that we still need. Ideally, diamond would be the best transistor material, but we don't know how to, boron doping's fine, but the other, converse doping can't do it. So anyway, Another thing I should mention is the energy in computation and communications. We use silicon. This is silicon MOSFETs. It's ruled the roost. CMOS silicon has ruled the roost for many, many decades. But people are beginning to consider ferroelectric materials, including perovskites, for both memory and logic units. A fellow who used to be at Berkeley, who I recruited to lead our so-called Sunshot program, Department of Energy, Ramesh, has founded Kepler Compute based on ferroelectric materials. He's now Vice President for Research at Rice University. And again, very quickly, he found that it's the ability to make the material in good quality that really counted. And so Ramesh then teamed up with Applied Materials, and this is Om, who is the Chief Technology Officer of Applied Materials. And within a year or so, they were able to make these perovskite materials with much better reproducibility and much better results in terms of performance. And so again, you see this, without materials development, you get stuck very quickly. And it really never gets to be commercialized. Okay, let's talk a little bit about energy storage. The best energy storage, in my mind, is a very old technology. When you have renewable energy like wind or sun, you can pump water up a hill. And pumped storage, raising water up from the bottom of the dam to the top of the dam, hydroelectric dam, is about 95% of all electrical energy storage in the world today. We will have to increase utility scale storage by several orders of magnitude, at least 2, 3 orders of magnitude. And if you have an existing dam, just replacing it with a more efficient turbine that goes both ways is the cheapest form of electrical storage. I would also give a shout out for Bill Nix's earlier work. I did this, I was beginning to think about preparing my talk yesterday, and so I said, what is Bill Nix famous for? I asked ChatGPT, and it comes back. Professor Nix is an internationally renowned scholar in the field of mechanical behavioral solids. He started his research career with a series of important contributions on high-temperature creep fracture of materials in the 1960s. And he goes on to give many, many more compliments. The need for even higher temperature materials, economical materials like higher temperature seals, remains, simply because you go to higher temperature, you can get more efficient in converting heat energy into electrical energy and back. But you can also think of then just storing excess renewable energy in the form of heat energy and not converting it back, just using it in industrial processes. The industrial processes, thermal heat is really inexpensive. It's usually supplied by natural gas. And if we have to get off natural gas, we need a much lower alternative. So there are other forms of energy storage. PHS is the pumped hydro storage, but people are also beginning to look at the production of hydrogen, synthetic methane, and all of these other things. Again, these rapidly become materials problems. Problems in electrolysis, getting rid of the very expensive materials still remains. In fuel cells, where you can take hydrogen and convert it to electricity, or you can take electricity and convert it to hydrogen. So one is thinking now, if you have excess energy, can you transmit electricity to a set of fuel cells that you make the hydrogen at the source, let's say the oil refinery or wherever, or the steel making plant, when we figure out how to use hydrogen to make steel and decarbonize a lot of the processes. So these are things, again, which are become materials problems. I should say that there is a good progress being made by another former DOE employee when in the time I was there, who is now working for the chief scientist for Bloom Energy, and they have about 75% lower heating value efficiency in converting electricity to hydrogen and back. And it's a materials problem. How do you make them last longer and longer and cheaper? Okay, let's talk about batteries. This is the energy density on the y-axis is energy per volume, and on the x-axis energy per weight. That green arrow is taking batteries where the Tesla is today to where it's going to be perhaps 10 years from today. Not only is the energy density going up, the cost is really come down. On the right-hand side, you see on the logarithmic curve the cost, and on the x-axis is how many units of batteries in terms of kilowatt hours or megawatt hours have been deployed. So this is the so-called learning curve, and once you establish a learning curve, you are exponentially improving as a function of the number of units you ship. And so the cost has really been dropping. In year 2000, where there wasn't much mass-produced batteries, $2,000 a kilowatt hour. By 2020, the production costs that OEMs like General Motors are willing to pay for a battery is less than $100 a kilowatt hour. And by 2030, it's going to be less than $50 a kilowatt hour. But there's an issue with all learning curves. There could be other things that stop the learning. And ultimately, one of the things that stop the learning is the availability of materials. As you begin to run out, it becomes an issue. And will we run out of nickel and cobalt? The answer is yes. Will we run out of lithium? The answer is yes and no. The fact that we're running out of cobalt, especially, and nickel, is already the EV manufacturers are shifting to iron phosphate lithium batteries. But what about lithium? It is possible, and this is some work by Chong Liu, who is a graduate student of Yi and then a postdoc with Yi and myself, who's now at the University of Chicago. She has figured out how to run a sort of a half battery, iron phosphate, and you can induce salty water to go into this iron phosphate, but it picks out lithium above all the other ions. And in one cycle, she was able to get, starting with a ratio of 1 lithium ion per 20,000 sodium ions, she could get 8 lithium ions and 1 sodium ion when you take the lithium and sodium out of this iron phosphate material. Whether it becomes practical or not becomes an issue because this is a two-dimensional device, and so it's a surface area. But the fact that it will be possible to take salty water, when you drill for oil and gas, you get a lot of salty water, sometimes 10 times more salty water than oil, but the lithium in the salty water is worth more than the oil. And so people are beginning to realize this. And I'm an advisor to Shell, Royal Dutch Shell, and I said, I hope there will come a time when you're looking for lithium and you find oil and gas and you pump it back into the ground. And extract the lithium, and you extract only the lithium and then you pump it back into the ground. Far less polluting than pumping lots of water up, letting it evaporate with all the yucky, polluting stuff. Just extract the lithium and stick it back in the ground. It becomes a materials question. Okay, so how can we improve the battery in terms of energy density? I mentioned we went cobalt oxide, which is used in your cell phones, is way too expensive, and nickel, manganese, cobalt mixtures in today's EV batteries also becoming too expensive. So you go to iron phosphate, possibly sulfur, but if you go to lithium metal, you can recover a lot of the energy loss of going to iron phosphate. So what's the problem with the metal battery is that in this cartoon, you have a lithium anode and a sulfur cathode. And in the electrolyte, the lithium is in the form of lithium stuck to a bunch of sulfurs. It could be Li2S8, Li2S6, S4, and so on. Now, if you begin to charge and discharge the battery too fast, there's a a protective layer between the lithium and the electrolyte called the SEI layer, solid electrolyte interface. And a little bump could draw more lithium onto this little bump because it's a higher electric field. It's no longer flat. You've got a little bump. And so the bump grows, it grows, and it forms dendrites. And that would short out the lithium metal battery. So is it possible that one could develop a material that actually allows lithium to pass very easily through this material, yet it's so strong it would prevent these bumps from growing? Okay, let's talk about decarbonizing agriculture. If you look over the history of how things went in terms of population, this is an article written by a Nobel laureate in economics, Robert Vogel, and he actually ties the progress of all the industrial revolutions and things like that to the agricultural revolutions. The first revolution started about 10,000 years ago, 12,000 years ago, when the climate got stable. And so when the climate got stable and didn't yo-yo between ice ages and warm periods, suddenly in about a half dozen places all around the world, within 100 years or so, agriculture developed. Okay, it wasn't that technology was not transmitted, it was reinvented in many places around the world, and it was due to a stable climate. So the agriculture was domestication of wheat, rice, cattle, as you see, yeast and other things. There's a second revolution. The second revolution is remarkable. It was not a technology revolution, it was a policy revolution. They said in England, you can fence off the land and you can use it for your private use and your neighbors couldn't use it. And because of that, it allowed capitalism to take root, and you can say, now I can make my land profitable, but if everyone can graze on my land, it becomes overgrazed. And so it was that, the development of natural markets and free of tariffs and transportation infrastructure that allowed the agricultural revolution to really take off. And then that spread. What's the third agricultural revolution? It's again a materials issue. It was the invention of the ability to make nitrogen-based fertilizers from nitrogen, ultimately from the air, from ammonia. And it was the Haber-Bosch process that earned Fritz Haber Nobel Prize in 1918 and Bosch a Nobel Prize in 1931 for the exact same thing, called the Haber-Bosch process. They decided it was too important, they should give him a Nobel Prize also. So the excuse was for his contributions in high temperature, high pressure catalysis, which was the Haber-Bosch process. So anyway, another part of the agricultural revolution is the crossbreeding of plants. So Norman Borlaug bred disease-resistant dwarf strains of wheat, and you can see his bred things with very, very thick, heavy kernels that did well and could survive fertilizer and irrigation. The combination of fertilizer and crossbreeding of plants meant that from 1960 to 2018, you can go from a population of 3 billion to about 7.4 billion, and the amount of land put under cereal production, the major grains, wheat, rice, corn, things like that, didn't increase. And so this is a product, this is a really profound third agricultural revolution. We've also been able to breed animals so they could grow very rapidly. If this full circle is the lifetime of a natural cattle or pig or chicken, this is when they're slaughtered. So, for example, cattle are slaughtered within a year and a half, 2 years, 1,800 pounds. Pigs, 22 to 24 weeks, and by the time they're 24 weeks old, they weigh 280 pounds. Okay, so very, very efficient. But the issue here is there was another unintended consequence, because as the world got richer, especially the United States, we started to eat much more meat, especially beef cattle. And if beef and dairy cattle were a country, because of the methane they burp out, it's largely burping of methane, they emit over 5 gigatons of carbon equivalent per year. So that's more than the EU plus Great Britain, and more than the United States, or comparable to the United States. And so the methane emission has become a very big deal. One is looking for solutions of the feed of cattle and other things to decrease the emission. You can also eat less beef, especially. Just as an aside, we have geoengineered the world through agriculture. If you put on a scale humans and the animals we eat on one side of the scale and all other mammals on the other side of the scale, wild or whatever, we're 95% of the mammal weight. So what else about agriculture? Well, we have fertilizer, the miracle fertilizer, but over 3/4 of the nitrous oxide is coming from agriculture and soil, and if you also include the manure and wastewater treatment. And so it is a big deal. But this is a problem, because how are you gonna, we need agriculture to feed a world of 8 billion, and we need fertilizers for this. Only very rich countries and people in very rich countries willing to pay the price for organic. It's possible, but the developing world can't afford that. And so what do you do? It could be a materials problem, it could be a biology/chemistry problem, which is essentially both. And so there's a development in the last couple of decades called synthetic biology. And what synthetic biology does is it alters the genomes of organisms, let's say microbes, and a company called Pivot Bio then develops the microbes. When these microbes are planted with the seed corn, they enter into a symbiotic relationship with the corn at the boundary of the root to soils, inspired by legumes, who would actually extract nitrogen out from the soil and use it as fertilizer. And so these microbes actually decrease the amount of fertilizer by twofold. Twofold is a good start, but you need to get rid of all the fertilizer, and it has to be done rapidly enough because different soil microbiomes have different properties. So it's a nascent technology, but it needs a little bit of goosing. I should also say, in terms of speeding up this progress, you can only alter one gene, one promoter at a time. Sometimes the solution would be 10 genes. And so it takes many years, 6, 8, even 10 years to actually develop a microbe and get it to high productivity. And so that long development time has meant that all the startup companies based on synthetic biology have not yet flourished. And most of them are have either gone bankrupt or hanging on with the skin of their nails or whatever. There's a hope that one can develop methods to inject a dozen genes into cells at once. And if you can do that, since you can type out the DNA and just do an experiment here and do thousands of experiments in parallel, you get combinatorially faster looking for a solution. And so that is certainly a target. In my own group, we're trying this with a nanoelectroporation method based on nanopore filters. But it's, again, trying to, if you consider materials and part of this microbes, it's part of the solution. Okay, so now, what about carbon dioxide? You saw in the earlier slides that we're on a pathway to get to about 3 degrees centigrade of carbon dioxide. And remember, in order to get to 2 degrees or even 2.5 degrees, you've got to stop all emissions of greenhouse gases. But since it's going to take time to decarbonize agriculture and several other areas, there's a feeling now, a strong feeling that you would need to actually capture carbon, not only from cement plants, steel, power plants, but also from the air. And you have to bring the price down to where it could be possible. Right now, it's $300, $400, $500 a ton to capture carbon dioxide from air, $100 a ton or higher in plants. If you think about where we're emitting today, you're actually talking about 10 to 20 gigatons per year of carbon capture and then stored. And the volume, it's sort of like taking this carbon that you're burning from the ground. You've taken fossil fuel, you burned it, and you have CO2, and then you want to put it back underground. Well, the volumes are comparable, which is huge. And that's another thing. The volume of CO2 that you're pumping, even if you're pumping it down into a density of nearly 1 gram per cubic centimeter, it's pretty high volume. This is a pilot plant which takes a modest amount of carbon dioxide from a coal-burning plant. What's the size of this? Well, the little things down here are cars. So maybe 25 feet by 25 feet by hundreds of feet to capture CO2 using amines, typically in water or nano-based. But when the amine captures the CO2, but to release the CO2 and then get it, you capture it, you put it in another tank, the stripper tower, you heat it up, it releases the CO2, the energy used to heat it up is a lot, and you have these very big structures. You're heating up not only the amine with CO2, you're heating up a lot of the stuff around it, like the solution. So for that reason, people are beginning to think, well, you know, if you put it on some sort of three-dimensional mesh, which you can attach amines to, is it possible to capture CO2 and when you heat it back up, you're heating back less stuff, and so it becomes more efficient. And a new class of materials called metal organic frameworks, pioneered by Omar Yagi at Berkeley, was a possibility, and George Simaju in Canada developed a MOF that can actually withstand flue gas environments. And another startup company, Svante, which I've been on the board of directors of for a decade, is now pairing up with BASF. BASF has learned how to make these MOFs in production volumes. And so that's another possibility. I should say that there's other ways to capture CO2. One way is people notice that if you change the pH of water from an acid to a base, if it becomes more and more basic, here's pH and the amount of total dissolved carbon content in the water. Going from 4 to 10 changes the carbon carrying ability by 4 orders of magnitude. So finally, I should say that the winner of the CO2 capture, which is absolutely necessary to stay below 3 degrees centigrade or even 2.5 degrees centigrade, crops we plant capture between 10 and 18 gigatons per year of CO2, and they convert CO2, solar-powered CO2, into biomass. But virtually all of it is recycled. We don't eat most of the biomass. And so if you can then consider taking the biomass we don't eat and we don't put back in the ground as fertilizer and somehow compacting it to the density of 1 or 2 and in little pellets so you can pipe it around in a kind of a fluidized thing, then you find that you can get into the gigatons or even tens of gigatons volume. The amount of storage is equivalent to municipal dumps. It's a lot, but it's possible. So, okay, let me conclude. So I've showed you where new materials can really transform the landscape. I didn't talk about materials. Fusion won't ever become commercially viable unless we solve the neutron damage problem, which we have not solved. And in a tokamak, you have scrapers that also get eroded very quickly. So, but let's go on and see, we've seen great progress in solar, great progress in batteries, continuing progress. So are we going fast enough? So if you look at the transition from fuel sources from wood, this timeline starts in 1776 to 2014, and we went from wood, first coal, and then we then began to shift to petroleum and natural gas, And more recently, there's nuclear, hydro, and other renewables. That little thin sliver up at the top of renewables, wind, solar. So that looks pretty good. So, except, oops, it looks like it takes about 60 years to make a transition, let's say from coal to oil and gas. But it's actually worse than that. This is the absolute value of the fuel we use as a function of time. And we weren't going from wood to coal to oil to gas. We were just adding new energy sources. Okay? So we do have a problem. So we're adding new energy sources. Yes, we're using less coal in the United States, but the developing countries are using a lot more of it because it is so inexpensive. And so I want to leave you with this very sad thought. We're still cruising towards 3.5 degrees. It takes a long time to turn the ship, and we haven't slowed up to where we're heading. And there's an old expression of Yogi Berra, if you don't watch out, you may get to where you're heading. And that's where we're heading. All right, thank you. Right. Yeah.
We should take a few questions.
Steve, it sounds like you've just made a strong case for research in geoengineering.
Yes. Well, first of all, agriculture is geoengineering on a very grand scale. So we've been practicing it for a very long time. I think the geoengineering of things like atmospheric geoengineering are possibilities. The first thought was sulfur dioxide, but that turns out it makes the ocean more acidic. It also is a greenhouse, you know, it's got a lot of bad things. And it disrupts the ozone layer. So there's still a lot of, you know, more durable oxides that are possible. I'm a big fan of geoengineering. Any roof, you make it white, and all the pavements, you make it white. That's geoengineering on a smaller scale. I think the further geoengineering of agriculture will become absolutely necessary, and to engineer the soils will become necessary. Whether we have particulate matter in the air, it takes about 1.5 years for it to come down. And if it could be shown to be benign, that would be good. The good news is you can turn it off because it's only up there for about 1.5 years, suspended with so-called Hadley currents, and then it comes down. But I think we will, you know, large capture of CO2 from the atmosphere is kind of geoengineering, right? And the agriculture, and plus natural photosynthesis, that's why the CO2 oscillates, but there's more land in the northern hemisphere than the southern hemisphere. And so all these things will have to be considered. When I was Secretary of Energy, it was thought we should be in an act of desperation. Since my time then to now, it says we're closer to desperation because of the slow progress. And when you look at all the things that have to be done, it's a real issue.
Well, we stand. Let's thank Steve.
Okay.
Well, now we'll have some closing words from our honoree, and he will be introduced by Professor David Matlock, Professor Emeritus at the Colorado School of Mines.
Thanks much. It's certainly an honor for me to have the opportunity to introduce the last speaker on this morning's or today's program, since I think it's now no longer morning. But it's truly an honor. When I first learned of the William D. Nix Lecture Program that the department set up, it was very clear to me that they chose the right person to which this should be named. In 2019, he wrote a summary of the department, and in 2019, many of us here today we here when we celebrated the 100 years of the Department of Material Science. And in that presentation, he talked about all of the outstanding faculty that have been through this department. But clearly, one of them stood out, and that was, he's the mainstay of the department, and that was Bill Nix. He started his career at Stanford in the late 50s. And here we are 8 decades later, and he's with us today. And so, you know, that's a truly remarkable achievement. Some people talk about career. Wally talked about his career in terms of years. This is decades. And then I did a little bit of math. That's 47% of the life of the university. 47% of the life of Stanford University, he's been on campus. Pretty remarkable. We've been treated today by the second program, which was truly outstanding, and I think it truly met the criteria and the guidelines that the department set out to bring material scientists together and understand the profession that we are all involved with. I note back when I entered Stanford in 1968, I entered the Department of Material Science. When I graduated from Stanford, thank goodness, it was the Department of Material Science and Engineering. And so it really embraced the complete need of the program. I want to take a note, just a minute here, and note that there's another special lecture program that has been set up in Bill's name. In 4 weeks at the TMS meeting in Orlando will be the 5th William D. Nix Award Lecture Program, a lecture that was set up and established and endowed by his PhD students, of which I mark myself as lucky number 13. And so that program was set up to really help bring forth what he has done in his career, and that's mechanical properties of materials at all scales. And clearly, when I was here, and Wally mentioned that, talking about structural materials, and then as life went on, he started looking at smaller and smaller things. And in today's lectures, we heard about atoms being set between atoms. I don't even understand that anymore. But that's where we are, and this is really quite incredible. And so in 4 weeks, we'll have this 5th one of these lectures that has come about. Bill is truly one of the few people that is both a member of the National Academy of Science and the National Academy of Engineering. And that really reflects his contributions to engineering education, which is really carried on by his students, as well as the scientific achievements he has made. Truly remarkable in terms of his broad-ranging impact on the global society. In his career, he has received numerous awards. We do not have time, and I will not list them all. However, I would like to take and highlight one specific award for which I am extremely proud. In 2001, his significant contributions to engineering and science were honored, in which he received an honorary Doctor of Engineering degree from the Colorado School of Mines. I think that's the pinnacle of his career. And so in that, I think I would like to invite Bill to the podium to make a few closing comments, or as Paul Harvey would say, the rest of the story.
Wow, what a great program. Many thanks, David, for such a generous introduction. I'll say a little bit about our time together. I well remember our good times together, really more than 50 years ago, as he implied, and also the trials and tribulations of your dissertation, in which you well remember. And you may even remember that we got hung up on how to describe experiments that you were doing. And like to carry out an experiment sounded like carrying buckets of slop to the pigs. Carrying out that doesn't seem very good. Or to conduct an experiment. But that sounds like conducting an orchestra. Well, what else? Or performing an experiment. But that sounds like the ballet. So I'm not sure. You remember this, right? And we were all hung up about which one of these. So I'm not sure what we settled on. But it set you off to a really great career. And I don't know if it's been fully said here. After David left Stanford, oops, dropped my water there. He became a professor at the Colorado School of Mines, which you already heard, where he was the Armco Foundation Fogarty Professor in the Department of Metallurgical and Materials Engineering, and significantly, Director of the Advanced Steel Processing and Products Research Center, which he founded, a major achievement. And I'll just talking about David, I'll say one other thing. He's the first of my students to be elected to the National Academy of Engineering. Now, so thanks also, Albert, and the MSc faculty for establishing this lecture. With Stan Whittingham last time and Steve Chu this time, you've set a very high bar. I'm sure you've thought about this. So what can you do for an encore? So they're aiming high, as you can already see. And thanks also, Alberto mentioned this, to Lisa and Chris and the rest of the MSc staff for putting together this program. It's gone very smoothly, as it often does. We appreciate that. And so Steve, is Steve still here? Yeah, there you go. It's really a great honor to me and for us for you to come here and have you deliver this, the Nix Lecture. And, you know, you couldn't give a better case for material science than Steve gave. So we appreciate that. So I'm now pleased to recognize you, welcome you as a card-carrying materials scientist. And so E mentioned some of your accomplishments. We'll now have to include that on your list of accomplishments as a card-carrying. That'll be included as one of your honors. Now, why do I say that? Well, listening to your lecture, that already justifies what I've just said. But I had looked through your most recent papers listed in the ISI Web of Science database, which you know very well. And I discovered that of the 20 most recently posted papers in the Web of Science, 12 of them were written with MSc faculty and their students and colleagues. And that list of postdocs, and that list includes Jen Dion, Yi Cui, Mark Brungersma, and Nick Paloche. And I only went 20 down in the list, and 12 of those were with material science. So welcome, Steve, to the club. I'll have to see if I can't find you a membership card one of these days, and so you can keep it. So thank you. Now, thanks all to Wally. Thanks to Wally, who was introduced by Alberto, and you heard about the tremendous work that he's done in the semiconductor industry, and you heard some of his earlier work. Now, Wally, speaking of clubs and the Material Science Club, Wally's been a member of the MSc Club for a long time, since he was a kid. And here I have something to tell you. When he was 18, that would be in 1965, he was still 18, I gave a course, Material Science 219, only I remember that number, solid state phase equilibria. And I used the book by his father, Frederick Rhines, and Alberto mentioned this, phase diagrams in metallurgy, and I used that as a text. And I'll just say a little bit about what I did in that. I tortured students on the intricacies of ternary phase diagrams and asking them to create isothermal and isocompositional sections of the diagram. And I like to point out, Alberto almost mentioned this, I like to point out that some of the three-phase domains in these ternary phase diagrams looked like the shape of the hood of a 49 Ford. Now, I guess it didn't go over very well. I got that mixed up there. I guess that wouldn't go over so very well now to make that analogy, but truth be told, it didn't go over very well then. But if you study those things, you'll actually see that it starts at a line and it comes down, and by the time it's a triangle down here, and that's exactly the shape of a, well, okay, that's another story. Now, you may know that, Wally mentioned some of this, but before he became an executive at Texas Instruments and later Mentor Graphics, as you heard a little bit about this, he really co-invented with Herb Maruska, who was the lead, of course, and Dave Stevenson on the blue light-emitting diode. And as he briefly there described, it's a light-emitting diode with, it involves magnesium-doped gallium nitride, and that was what they did. And the blue LED that was based on gallium nitride was later perfected, as you heard, by Akasaki and Amano and Nakamura, and they received the Nobel Prize in Physics for that work, but acknowledged the precursor work. So, speaking of membership cards, Wally doesn't need an MSc membership card, so I need not give one to him. So thanks to Laura, Leora, and Felipe for really showing us the vibrancy of the next generation of material science. It's great to see that our department has such a bright future. And just to be brief, thank all of you for coming to this affair, and especially my former students, many of whom collected in my house, our house, yesterday in the rain and then without power later. My former students, postdocs, and visitors And thank you all for coming for this occasion. And finally, thanks to the power of my family, Jean, and my family for their continuing support. And I'll just mention that the get-together we had yesterday, our kids and really Jeff and Cynthia and Jeff's wife, Kat, really were the drivers in making that all happen. So thank you very much also, and thank you all.
Well, thank you, Bill. Thanks, everyone. So now lunch is served, but remember there is the student posters on the opposite side of the hall. You will really get a great glimpse at what our department has been up to in the past year. So thank you, everyone, for coming. Thanks to all the speakers, sorry. And then now is a fun part where we get to reconnect and chat.